then usually this is a closed contour in the PV diagram. So the pressure and volume starts at some point and it returns again to the original point once we have a strictly periodic motion of our star or the mass element within the star. And we convinced ourselves that the work done by this element or consumed by this element is simply the integral over the path in the PV diagram. So this is the integral over one cycle, integral P dV over one cycle of pulsation. So this is one mass element which is considered here, and the differential work integral denoted by V dash then tells you whether at this position or by this mass element within a star, energy is either produced, meaning energy is transferred from heat to mechanical energy, or vice versa, which energy is dissipated from the mechanical energy and goes into heat. These are the two ways. Okay, so we already discussed this. So during the pulsation, the kinetic energy or the mechanical energy is increased or dissipated per mass at the rate. We can now rewrite this PdV work in terms of the change of the mechanical energy with time of the mass element. This is given by the change of pressure or the pressure, the Lagrangian pressure perturbation times the time derivative of the Lagrangian volume, or alternatively the Lagrangian density perturbation. Well, a suitable average over one, of course we have to average over one circle, because locally this does not have a meaning, so over one circle averaged, or taking a suitable ensemble average over the pulsation of over pulsating equivalent pulsating configuration, then we end up with the following form for the differential work integral. It can be expressed in terms of the eigenfunctions, so to say, in terms of some components of the eigenfunction, namely the eigenfunction component Lagrangian relative Lagrangian pressure perturbation and relative Lagrangian temperature perturbation. And then if you perform the analysis, then the differential work integral, that means the energy dissipated or generated per integration interval per mass of the mass element, is then proportional to the imaginary part of the product of the pressure perturbation times the complex conjugate of the temperature perturbation. Okay, so if W dash, the differential work integral, is bigger than 0, then mechanical energy is provided. That means the perturbation or the oscillation is excited, or in other words, it is a driving region. It drives the pulsation. If the differential work integral is smaller than 0, then mechanical energy is dissipated. This is a damping region. This leads to a damping of the oscillation. This, of course, is the normal case. Usually the energy is dissipated and energy is taken out of the pulsation. That means the mode or the oscillation is damped and its amplitude decreases, and ultimately you end up with the hydrostatic model you have started from. Okay, this is per mass or per integration interval. We have used log P naught as the independent variable. So this is the energy per interval in log P naught. And once we would like to know whether we have an excited or a damped mode, then we have to sum up all the driving, all the mass elements, and summing up over W dash of the driving regions and the damping regions, and then we get either a positive value of this integral. This means the driving regions overcome the damping regions, and we have on total we have a mode which is excited, and if the integral is negative, then the mode will be damped. This is the normal case. So we have instability once the integral over W dash is bigger than 0, and stability or damped mode once this integral is smaller than 0. In that way, we may identify within the star those regions which are driving and those regions which are damping. Okay, well, this gives you the position where a mode is excited or damped, but it does not provide any explanation or mechanism for the instability. The second step would then be, once we have a driving region, what is special with the other quantities appearing in our equations? For instance, how does the derivative of the energy generation rate behave in this region, or how do the derivatives of the opacity behave in that region? And then to correlate the driving regions with other quantities like derivatives of opacity and energy generation rate. So keep in mind, this differential work integral only tells you where a mode is excited, but not what the mode, what is the mechanism that excites the mode. Okay, so W dash might be a useful tool to identify damping and driving regions within the star, and it can give you hints on the instability mechanism. It does not give you the instability mechanism, or it does not tell you what is the instability mechanism which is present. Keep in mind also, this analysis is based on the assumption that our star or the excitation of our pulsations are done by a Carnot type process. That means the instability is caused by transfer of heat energy into mechanical energy. So let's consider two examples. The first one is a 0H main sequence star of 87 solar masses, and we consider the first overtone, which has a frequency of 2.43 in our normalization, and which is unstable with a growth rate of minus 1.9 times 10 to minus 3. And for the second model, we consider a 120 solar mass 0H main sequence star, which has a frequency of 1.3 and which has a very low value of sigma I of minus 1 times to 10 to minus 6. So this is a very weakly unstable fundamental mode in the 0H main sequence star with 120 solar masses. So let's go to the 87 solar mass star. Here as a function of log p, we have the W dash, and we see here there is a domain where W dash is negative, so this is a driving region, and this here is this is a damping region, and this is a driving region. And if we take the integral over this function, then the integral is positive, so this area under the curve, this positive, the area under the positive value of the curve is bigger than the negative one, so this corresponds to an excited unstable mode. Now once we relate this domain where driving occurs with the properties, the other properties of the stars, we observe that exactly in this domain or in this region we have positive values of the derivative of kappa with respect to temperature. So it seems that this driving region is caused by positive values of the derivative of the opacity with respect to temperature. Okay, now let's go to the 120 solar mass star. Well, again, we have a very similar behavior here in the outer part of the star. close to the surface of the star. Again, as a function of log p, we have the differential work integral. Again, we have a negative part, this is the damping region, and we have a positive part where the differential work integral is positive. And there are some negative parts here as well, so this leads to damping, and the integral over the entire differential work integral is again positive, but it's weakly positive only. And well, there is a second part very close or at the center where the differential work integral is positive, and once we look what is going on there, then we find that the derivative of the energy generation with respect to temperature is positive there. So this is the positive value of kappa T is associated with the driving region, and the positive value of epsilon T is associated with the second driving region. So this is called the kappa this is the kappa mechanism, which is responsible for driving, and this is the epsilon mechanism, which is responsible for driving. Well, the weakness of this instability is mainly caused by the weakness of the epsilon mechanism, and what you see here at the same time where the epsilon mechanism is present, we also have the kappa mechanism present. So there are two mechanisms which compete with each other, and it's always the kappa mechanism is always present, even if the epsilon mechanism also in those cases where epsilon mechanism is present. So they are competitive effects concerning the driving. Okay, so what we saw here, this is the result. Well, damping and dissipation is the normal effect, and driving is found once either kappa T is bigger than 0, then this is called the kappa mechanism, and if epsilon T is bigger than 0, this is the epsilon mechanism. Both modes are affected by the kappa mechanism. As you saw, both modes show driving in those regions where kappa T is bigger than 0, but only the fundamental mode showed a driving region associated with positive epsilon T. Well, once the epsilon mechanism is working, it is extremely weak. So the growth rates obtained from the epsilon mechanism are very small. This is not surprising because the epsilon mechanism should work on the nuclear timescale. Nuclear timescale is much bigger than the dynamical timescale. So the growth timescale is usually, if it's caused by epsilon mechanism alone, then the growth timescale is proportional to the nuclear timescale. It is only found, this is a result which I just quote here, it's only found in the very vicinity of the 0H main sequence. If you go off the 0H main sequence, the epsilon mechanism will no longer work, and you need masses at least of 60 to 150 solar masses to see this epsilon mechanism. Moreover, it is opacity dependent. That means the opacity plays at least an equal role as the energy generation for having an instability. So the epsilon mechanism always competes with the kappa mechanism. So there is a competition with much stronger instabilities in general. So epsilon, keep in mind, epsilon mechanism is very weak. The time scale on which the epsilon mechanism operates is nuclear time scale. The growth time scales are very, very small. And it is restricted to the very vicinity of the 0H main sequence. Which means, if you compare it to the evolutionary time scale of the star will take the star the same time, or the time for the star to evolve off the main sequence or out of the epsilon instability domain is comparable or even shorter than the time it needs for the instability to grow by a factor of E. That means this epsilon instability, it is present. It is certainly correct to deal with the epsilon mechanism, but it is of academic interest only because this star will move out of the instability region before the instability can grow significantly. So actually this was the first instability mechanism proposed by Eddington. He is right, of course, the effect exists, but it is not of interest for realistic stars because the timescales are simply too long for this instability to grow. Okay, so now we would like, of course, to have the next step a intuitive model for this epsilon and kappa mechanism, and it's already been addressed yesterday, partially by Professor Yadav. Let me just briefly comment on an intuitive model for this kappa and epsilon mechanism. Well, we have to start with, once we consider this mechanism, we have to start with a periodic motion or a periodic cycle within our star. So consider our star performs an adiabatic pulsation. So it's a strictly periodic motion. The amplitude stays constant and the star returns after one pulsation cycle. The star returns to its initial state. Okay. Well, all these Carnot type heat engines require a periodic, a cyclic motion, like a diesel engine or a fan, a aircraft engine. All these engines, they need a cyclic motion to start with, and the cyclic motion here for the star might be considered to be the adiabatic pulsation of the star with constant amplitude. Well, what happens in the state of maximum? Well, we have a star which pulsates. We have compression and decompression of the star. So in the case of a radial pulsation, the star changes its volume and therefore it has a point of maximum compression. This means the highest density corresponds to maximum compression, and since it's an adiabatic pulsation, then also the pressure will have a maximum. What about the temperature? If you have adiabatic motion and you have compression and decompression, density changes in the first place, then pressure changes. What happens to the temperature in adiabatic motion? Temperature at the phase of maximum compression will be maximum. So we have a temperature change during adiabatic changes of state. So in the phase of maximum compression, we will have a phase of maximum temperature. If then if you then insert or if you release additional energy in the phase of maximum compression, that means you put in energy for instance by igniting fuel in a diesel engine or in an aircraft engine at the phase of maximum compression, you insert or ignite some fuel, then you add up an additional amount of energy, you deposit an additional amount of energy at this phase. An additional amount of energy will give you an additional increase of temperature in excess of the adiabatic temperature increase, and this temperature increase, this additional temperature increase will then give you an additional pressure increase, which in addition to the adiabatic pressure restoring, will give you an additional restoring force from the additional pressure which is caused by the ignition of fuel and so on. So this was the model which Eddington proposed in the initial phase, or in the once he studied stellar pulsation and the excitation of stellar pulsation, and that's what is done once we consider the epsilon mechanism. So if we have an additional energy release in the phase of of maximum compression caused, for instance, by adiabatic motion. If we have additional energy release, for instance, by nuclear processes, and these are the processes we have in mind, then we have an additional increase in temperature and pressure, and we have an additional restoring force over in excess of the adiabatic restoring force, and this means that then the amplitude will increase and we have an instability. What we need for that is that with increasing temperature or with at the phase of maximum compression, we have an additional energy release. That means that the change of the energy production rate, the energy generation rate, epsilon must be positive. Epsilon t must be positive. The dependence of the energy generation must be such that the energy generation increases with temperature. Then this diesel engine or turbofan engine mechanism will work. Okay, so this was the original description of epsilon mechanism by Eddington, and we saw, well, it seems to work. It is actually a mechanism which has to be discussed for stars, but it is only of academic interest because the timescales are too long for this instability to grow. Well, another mechanism which we have already seen is the kappa mechanism. Well, this works in the following way. If the opacity increases with temperature, that means if in the phase of maximum compression and the phase of maximum temperature, the opacity is increased, kappa t is positive, then the material, the stellar material, reduces the transparency with respect to the transport of energy. Increased opacity means the transparency is reduced. That means that the radiation coming from the interior is damped up at such a zone and needs to be stored somewhere. So radiation comes from the interior. Opacity is increased in the phase of maximum compression, so it has to stay there. That means the heat has to be put or deposited in the corresponding mass element. So once this heat is to be stored, we have an increase in temperature and pressure, and then similar to the epsilon mechanism, we have an additional restoring force, and in addition to the adiabatic restoring force in that phase. Again, this leads to an amplitude increase and to an instability. So this is the intuitive model for the kappa mechanism to work. We start with a cyclic motion, for instance, from an adiabatic pulsation, and then in the phase of maximum compression, we obtain an additional restoring force, which is caused by the deposit of additional energy, and this additional energy comes either from an increased nuclear energy generation or by damming up the radiation there, which then needs to be stored at the respective mass element. Okay, that's the intuitive model for kappa mechanism and epsilon mechanism. Epsilon mechanism is of academic interest, and the mechanism which is responsible for all the classical pulsating stars is actually the kappa mechanism, and it requires a positive derivative of kappa with respect to temperature. Okay. Well, again, to summarize, epsilon mechanism only close to zero-H main sequence is very weak. Growth timescale competes with evolutionary timescale, and therefore it's only of academic interest. I should note here perhaps that epsilon mechanism has in former times been discussed always with the maximum mass a star can have, because people have considered the epsilon mechanism along the main sequence, and they found these epsilon mechanism sets in at masses around, well, it depends on the author and it depends on the opacities people have used, of the order of 100 solar masses, and this was thought that the epsilon mechanism, this instability, is responsible for setting an upper limit to the mass. This is of course no longer true, because the star has evolved already out of the instability domain before the instability is able to grow by a factor of e. So what people have ignored is the weakness of this instability, probably because they couldn't calculate these small rates, and they haven't considered the fact that the epsilon mechanism is only restricted to the very vicinity of the 0H main sequence. But still today, from time to time, you find in the literature people are talking about the epsilon mechanism and its relevance to the stability of star. So be careful. The epsilon mechanism does exist, but it does not have any relevance for realistic stellar models. Okay, the kappa mechanism is working for kappa t bigger than 0. In general, the derivative of kappa with respect to temperature is negative, so this is the exemption. Kappa t bigger than 0 occurs only at certain stages or at certain domains of the temperature range, and it is responsible for the majority, for the excitation of pulsation of the majority of stars. So where does this where do regions or where do temperature ranges occur where kappa t is bigger than 0? Well, let's have a look. This typically occurs, we have already seen this diagram. This is a cut through the temperature density plane. It plots, or what is given is kappa, the opacity, as a function of log temperature for some constant density. And what you see here, usually the opacity decreases with temperature, but there are, here it decreases, but there are 3 domains in temperature where the opacity increases with temperature. This is here, here, and there. And what causes these 3 maxima in opacity? These are ionization processes and the contribution of heavy elements. So this is hydrogen and first helium ionization, this is second helium ionization, and this is the contribution of the heavy elements. So these three slopes, these 3 positive slopes, may give rise to a pulsation, to a class of pulsating star, and actually this is true. This is the branch which is responsible for the Cepheids, for the delta Cepheids, and this branch, for instance, is responsible for the pulsation of beta Cepheid stars. Okay, so what we have, there are 3 domains where kappa t is bigger than 0, hydrogen, helium, helium-2 ionization, and the contribution of metals. And these three processes give rise to the excitation of pulsations of various stars. Here, maybe I can get this a little bit smaller. Can you reduce the size? Thanks. That should be okay. Okay. This is an HR diagram where the different classes of stars have been inserted. Logarithm of luminosity against the logarithm of temperature, high temperature on the left-hand side. The dashed line is the main sequence, and the hatched regions are the domains where the various variables are found. The most prominent variables are the delta Cepheids. They are found in a strip indicated by dashed lines here. This strip also contains the RR Lyrae star, the delta Scuti stars, And if you extend this strip to the white dwarf regime, then also there are some white dwarfs found which suffer from instability caused by the kappa mechanism, and this is the kappa mechanism which is due to the helium, the second helium ionization. So you can directly relate the positive kappa T values in the opacity diagram with the excitation of a certain class or a group of certain class of pulsating stars. Then you have at higher temperatures, of course, then also at higher effective temperature, you have the beta Cepheid star. They are caused to, they are excited by the heavy element opacity bump, by the positive kappa T related to that maximum of the entropy of the opacity, and the slowly pulsating B stars belong to that group. Also, there are some stars which suffer from the kappa instability due to heavy elements. These stars on the right hand side, they may be, it's not very clear, they are also affected by convection. They're the first opacity maximum due to hydrogen helium ionization plays a role. So you clearly can see this is kappa mechanism by helium 1 by a second helium ionization, possibly hydrogen ionization, and these stars by the heavy element opacity bump. Actually, these, I already told you the story about beta Cepheid stars. Before people have calculated correctly the heavy element opacities, there was no reason or there was no model or explanation for the pulsation of beta Cepheid stars, and people have invented exotic models including rotation, magnetic fields and so on to get these beta Cepheid stars pulsating, and once they came up with the correct opacities, no problem was left. The beta Cepheid stars pulsate because there is an additional opacity bump due to the contribution of heavy elements. So all these stars have been found or have been explained. Their pulsation has been explained once the opacity were calculated correctly in the mid-90s of last century. Okay. Well, finally, we use usually the period. You know, Cepheids are used for distance determination, and for the distance determination, we make use of the period luminosity relation. So, if you know the period of a pulsating Cepheid, you can derive, or you have the, you know its absolute magnitude or its luminosity, and of course we would like to know how this period luminosity relation may be justified. What we observe here is that the excitation of pulsations in the instability regions for Cepheids is a narrow strip in the HR diagram. So this narrow strip might be parametrized or might be described by a relation between effective temperature and luminosity. So the conditions, the proper conditions for the excitation of Cepheids by the kappa mechanism due to the second helium ionization may be described in terms of a luminosity temperature relation of the strip, the instability strip in the HR diagram. Okay, so to somehow motivate the period luminosity relation, we start off with considering or with stating that the instability strip is given by a temperature luminosity relation. Well, Stefan Boltzmann's law is of course valid in the entire HR diagram. Once the temperature is only a function of luminosity, then according to Stefan Boltzmann's law, the radius will be a function of luminosity only as well. Now we know that all stars have to satisfy the mass-luminosity relation. So if this means that the mass is also only a function of luminosity, then we know then the density is maybe approximated by mass over radius cubed. And if mass is a function of luminosity only and radius is a function of luminosity only, then the density is a function of luminosity only as a consequence. Now we know there is a famous period density relation. That means the period of the star goes with rho to -2. There's no secret behind it. It's simply the dynamical timescale which is responsible or which governs the pulsation of the star. So if the density is only a function of luminosity, then the period will be a function of the luminosity as well. So this is a motivation how the period luminosity relation may be justified, or how we get this period luminosity relation. And this period luminosity relation is one of the most important tools to determine distances in astrophysics. Now we have arrived with the kappa mechanism as the mechanism which is responsible for exciting the pulsation, and then inserting all the physics or all the formulae or all the relations we know from stellar physics or instability strip. We have made use of Stefan Boltzmann's law, mass luminosity relation, then period density relation, and we finally end up with a period luminosity relation which can be used to determine distances. Okay, now we've considered the standard mechanism for exciting stellar pulsations. Well, this is mainly the range or the regime with, I don't need it expanded. This is the range or the regime of stars which are moderately luminous. And what we are doing now, we will extend this diagram towards high luminosities, or in other words, to high luminosity to mass ratio. So we will go to the upper end of this diagram. These are the classical pulsators driven by kappa mechanism here, and we will go to stars which are much more luminous and which have much higher luminosity to mass ratios in terms of solar values. So luminosity to mass ratio is given usually in terms or in units of the solar luminosity and the solar mass. So luminosity to mass ratio means that the luminosity to mass ratio of 10⁴ means that luminosity in units of solar luminosity divided by mass in units of solar luminosity is of the order of 10⁴, or of any other value given. Okay, so we go to stars and consider pulsating or unstable stars in the upper part of this HR diagram. Okay, this will be done in the next file. So first of all, where are these strange modes found? What are the stars we are considering now? I promised you these are luminous stars, or in other words, not luminous stars, which does not mean these stars are massive, but their luminosity to mass ratio is high. The first example for the occurrence of these strange modes are the so-called hydrogen deficient carbon star or extreme helium stars. They are also called prominent example is the star R Coronae Borealis. So this is the prototype of hydrogen deficient carbon stars. The chemical composition of these stars is almost zero hydrogen. They almost consist completely of helium, carbon and oxygen. So it is hydrogen deficient means there is almost no hydrogen. Well, when one can represent models for these stars, by following the evolution of a generalized main sequence. Generalized main sequence means we are constructing now main sequence models using an initial composition which does not contain hydrogen but which contains only helium. That means this main sequence is defined by the ignition of helium rather than of hydrogen. So it's a helium main sequence which we consider, and we start off the evolution of these stars by requiring complete or essentially helium content and a little bit of carbon. So the evolution starts off the helium main sequence, and we follow the evolution then of this so-called helium star. How does it look like? Well, sorry for the quality of this picture. It's pretty old. So here is the HR diagram for the evolutionary track of this guy. So the effective temperature ranges from 4.8 to 3.4, and the luminosity, this is the evolutionary path of this star. We see here the helium main sequence phase, and then a helium shell burning phase, and in this phase the luminosity becomes very high, and the models we consider for stability are the models between these two temperatures. You see the luminosity here is around 10 to 4, and the mass of this object is 0.9 solar mass. So this guy has a pretty high luminosity to mass ratio. These are the models which are considered in the range of, say, 4.3 to 3.6 around log TF values. Okay. What do we find here? Well, these are the models which we consider for stability, and what we find if we perform now a stability analysis and look for the modal diagram which we determine, then we find the following result. Okay, here maybe we can get a little bit smaller here. So as a perhaps a little, okay, thanks. So along the evolutionary track, so we take models along the evolutionary track, and they are labeled with the effective temperature between 3.6 and 4.6 here. And sigma r, the real part of our eigenfrequency, is plotted as a function of model or of model parameter, or here in terms of the effective temperature. What we observe here is, well, there is a sequence of modes which is more or less equally spaced and which does not depend very much on the model. These are the modes which we expect for any ordinary acoustic resonator. Like for an organ pipe, we would expect an equally spaced spectrum of eigenfrequencies, and these should not depend very much on the model parameter, because we have accounted for by our normalization for the period density relation. So the modes should in any case follow the period density relation. So this relation is also already accounted for, and because we have accounted for the period density relation, we should have a weak dependence on stellar parameters of these modes. So these modes are expected, but what is not expected is some modes which have a strong dependence on stellar parameters and which cross these modes. So here is a mode denoted with Roman A. There is one with Roman 2. There is a mode with Roman 5, which have a strong dependence on stellar parameter and which cross the spectrum of the other modes, the normal modes which we expect in any case. So what about the imaginary part of these guys? Well, associated with mode 1 here are in fact instabilities, and that makes these modes very exciting. Not exciting the star, but exciting for us. So So the mode 1 is, the imaginary part of mode 1 is negative, so this corresponds to instabilities, and these instabilities are in fact not weak, but they are of the order of the dynamical timescale. So they range up to minus 0.25 here. So that would we would consider this as a dynamical instability. So it grows on very fast, on very short timescale, and there is an additional mode, the mode 5, which is also a member of this strange, or of these additional modes, which has an even higher growth rate of minus 1.5. So, well, the exciting thing about this is there are additional modes which we haven't expected, and moreover, these modes are unstable and leads to an excitation, or may lead to an excitation of modes. Maybe you see here that this is not a monotonic line here, but this line has some maxima. So it seems there are some maxima hidden behind in the growth rate, hidden behind this mode denoted with Roman 1. Okay, so let's go back. Well, the observation or the result is there seem to be additional modes, and because nobody knew what to do with these modes, because they are not expected, they have been called strange modes. There's nothing behind, no secret behind it. Strange modes are additional modes. Well, for some times people have tried to define it in terms of physical classifications. This has failed. Some people have said the strange modes are secular modes. That means they are thermal modes. But because some of them are also strongly damped. But here we have the example that these strange modes, these additional modes, are actually excited or are unstable. So there is up to now no clear definition, no mathematically strict definition of the term strange modes. I would like to address as strange mode any mode which behaves unexpectedly. So anything that is unexpected or is not covered by the normal behavior of an ordinary acoustic resonator like an organ pipe, anything that deviates from an organ type like spectrum is addressed as a strange mode. Okay, so well, the second part, strange modes are often, not always, associated with strong instabilities, and the growth rates are in a dynamical regime. Sigma I is of the order of minus 0.2 or even smaller. The question then, of course, is, are these modes, and this for a long time people have thought they are of thermal origin. Actually, this is not true. They are of mechanical origin. So we will come to this point later on, and we'll see that they are not of thermal origin, but they are of mechanical origin. Okay, so hereafter strange modes are denoted, or we call strange mode any additional modes in addition to what we would be expected from an ordinary acoustic or resonator like an organ pipe. What we observe once we compare these stars, these extreme helium stars, with normal stars, with normal I would consider or denote a Cepheid, well, is that the ratio of thermal to dynamical time scale is significantly smaller than for normal stars. This is associated with the fact that the luminosity to mass ratio here is bigger than 10 to 3, and in some cases it's also already of the order of 10 to 4. So let's go to the run of the we have already seen this diagram. Here we compare the ratio of thermal to dynamical time scale as a function of position within a star for a normal star, a Cepheid, and a hydrogen-deficient carbon star. You see this ratio increases once we go to the center, so close to the center all the pulsations behave adiabatically, and close to the surface this is of order unity. Their non-adiabatic effects come into play. Well, for the Cepheid, this domain where the thermal timescale is of order unity or even less is much smaller than for the hydrogen-deficient carbon star. For the hydrogen-deficient carbon star, this ratio is smaller, and the domain where this ratio is smaller than unity is also bigger. So when property of this hydrogen-deficient carbon star is that the ratio of thermal to dynamical timescale is much significantly smaller than for normal stars like Cepheids. That means, well, concerning the comparison of the adiabatic approximation and the full problem, well, for these stars we expect significant deviations once we do an adiabatic analysis, or if we compare an adiabatic analysis with the full non-adiabatic analysis, because these stars seem to behave or seem to deviate from adiabatic behavior, because the domain where the thermal timescale is small is much bigger. So we expect adiabatic and non-adiabatic analysis to differ from each other, and well, to provide significantly different results. The adiabatic approximation is expected not to be satisfied, as for instance in the Sun, where adiabatic approximation is a pretty well defined and well satisfied approximation. What goes along with the ratio, the small ratio of the thermal to the dynamical timescale, is that the contribution of gas pressure to total pressure is usually smaller than for the ordinary stars. If we write the pressure as a sum of gas pressure and radiation pressure, then the ratio of gas pressure, the contribution of gas pressure to total pressure, is significantly smaller than one which goes along with small thermal timescales. So there are two properties which we need to mention, or which are special with these stars: small thermal timescales and small contribution of gas pressure, or in other words, dominant radiation pressure. Radiation pressure is important for these stars. In the same time, the thermal timescale are small compared to the dynamical timescale. Okay, so this is one example for strange modes, for the appearance of strange mode. Well, you already know this diagram. I have plotted here the ratio of thermal to dynamical timescale for two massive stars, and we see the same behavior. Large masses correspond to high thermal timescales, and once we reduce the mass, the range where the thermal timescale is small is bigger for the low mass stars compared to the 60 solar mass star, where the domain where thermal timescale is small are only the outermost 10%, whereas for the 24 solar mass object it's almost half the radius. Well, and for this example I've already brought the ratio of gas pressure to total pressure, and you see for the 60 solar mass star the contribution of gas pressure never falls below 10%, whereas for the 24 solar mass star associated with a small thermal timescale, the fraction of gas pressure in the star can become much less than 0.1. So the small thermal timescales are often associated with small contribution of gas pressure, or alternatively with dominant radiation pressure. Now, well, once the once the strange modes in hydrogen-deficient carbon stars have been identified, a short time after that, Wolf-Rayet stars have been considered, and they are found to be the most extreme example for these additional or strange modes. Well, also the Wolf-Rayet stars are characterized by the same properties as the hydrogen-deficient carbon stars, thermal timescale divided by, or the ratio of thermal to dynamical timescale is much smaller than unity, and the contribution of gas pressure to total pressure is also smaller than unity for a large fraction of the envelope. Well, the standard representation of Wolf-Rayet stars are again generalized generalized main sequence models. They are helium 0H main sequence models. So if I will show a sequence of models, then this is the is a helium main sequence. These are helium main sequence models where the lowest luminosities are corresponding to the low masses, and the highest luminosity correspond to high masses. So this is a generalized main sequence, so putting a star with no hydrogen and essentially helium, carbon and oxygen on the position where helium is just ignited at the center. This defines the helium 0H main sequence, and the helium 0H main sequence has as a parameter the mass. So log L against log TF, and defining the position where helium is starting to burn, then this gives a sequence in mass, and this is M. Here on the bottom of this sequence, M is small, and here is M is high. So they are represented by helium 0H main sequence models. Okay, now let's have a look what the stability analysis with respect to radial perturbations, non-adiabatic stability analysis with respect to radial perturbations, what the result is. Just take the upper part. Well, here, this is the bottom part of this is now the real part of the frequencies as a function of mass along the main sequence. This is the bottom of the main sequence, and this is the top of the main sequence, ranging from 3 to 18 solar masses. Okay, so the real parts of the frequencies show a type of spectrum which we expect. We have a set of more or less equally spaced modes or frequencies with weak dependence on the stellar parameters, with weak dependence on mass. But superimposed on these modes, superimposed on this normal spectrum is an entire set of modes whose dependence on the parameters on mass, on the parameters of the star here, the mass, is much stronger, and their frequency decreases with mass, thus crossing the spectrum of the ordinary mode. So we have two sets of modes here, one of which we expect, and the other one which stronger dependence on stellar parameters, which cross these modes, and which is there in addition to the ordinary spectrum. So we call them unexpected modes. These are strange modes. Once these modes are unstable, they have been denoted in this diagram with thick dots. The tiny dots correspond to damped modes, to stable modes. So if we consider now the imaginary part belonging to that, well, what we observe then is the following. Well, we have lots of modes which have positive values of sigma I. These are stable, and these are essentially the normal modes. All the normal modes are stable and have positive values of sigma I. But once these strange modes enter the diagram, then they seem to come in a almost complex conjugate pair. So there is one strongly unstable mode, so one strongly mode in the pair having growth rates or having sigma I values of -2, and at the same time, once this appears, also a mode with the corresponding damping appears. Well, these modes actually have almost the same real part, the same frequency. It is not that obvious because below or close to these thick dots, which denote the unstable modes, there is a tiny dot which belongs to the mode with the almost complex conjugate value of sigma I. So these actually, below these lines, or these lines denote two modes, one of which is unstable and one of which has a high damping rate, and they appear in the imaginary parts as complex conjugate pairs. So the result is these are the ordinary damped modes, and these are the modes which appear in this diagram, one having a negative, one having a positive value of the imaginary part, and they are almost not perfectly, but they are almost complex conjugate symmetric. Well, perhaps you can see in this diagram another point. Well, it seems, well, we would call this, for instance, we would call these ordinary modes, but what happens, what seems to happen is that these modes seem to merge, and then they generate, by merging, this pair of complex conjugate modes. That seems to happen here as well. There are two modes which seem to merge to form the strange mode, and then the strange mode goes depends stronger on the stellar parameters and goes that way. So at a few places it seems that these strange modes seem to emerge from the ordinary spectrum. Okay, so this is what we find once we consider helium-0H main sequence models for to represent models of Wolf-Rayet stars. Okay. Well, I'm supposed to stop here. Yes. Then we will continue at this point. Thanks. Okay, let's continue. And let's continue by mentioning another result concerning the strange modes in Wolf-Rayet stars, because we have also done non-radial, non-adiabatic computations for a Wolf-Rayet star. So the model we are considering is a helium 0H main sequence star with 0 hydrogen content, 0.98 in mass helium, so it's almost a pure helium star with 2%, that means solar metallicity. The star has 16 solar mass. It's one of these objects which we have considered before, but now we are applying non-radial perturbations to our model. It's a single stellar model, and we consider the spectrum of eigenfrequencies as a function of harmonic degree. So the highest harmonic degrees we have here is 300, and it goes to 0, meaning radial perturbations. In the left diagram we have the real value of the eigenfrequency. In the right part, in the right panel, we have the imaginary part of the eigenfrequency. Now what we observe here, it's also a very complicated and bewildering diagram which we obtain here. For simplicity, let's start at very high values of the harmonic degree, 300. Well, what we observed once we look at the high harmonic degree is a spectrum like we expect for an ordinary acoustic resonator. It has a fundamental mode here, or mode which we call a fundamental mode. It's of course a fundamental P mode, and then we have a sequence of more or less equally spaced eigenfrequencies, so the spectrum looks like that of a normal organ pipe. All these modes here are damped, and this damping rate here amounts up to, say, 0.5. This is this bunch of lines corresponds to the damping rate, the intrinsic damping rate of all these modes. Now, if we decrease the harmonic degree, we observe that these modes merge and form an almost complex conjugate pair. This happens here, 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 and so on. It obviously is not restricted in order to some maximum order. So this merging of modes, thus forming a complex conjugate pair appears up to very high radial order of the modes. You see the almost complex conjugate symmetry here. Well, there is a dynamically unstable member of this pair. So, for instance, taking this pair here, then it merges somewhere around 150. So, and then we have a complex conjugate pair which increases its growth and damping rate once we approach L equals 0. So L equals 0 seem to be the spherically symmetric perturbations seem to be associated with the highest growth rates. Okay, well, complex conjugate symmetry contained in here. The highest unstable modes appear around here between 250 and 300. So we observe the same phenomenon here, but the phenomenon of the strange modes for Wolf-Rayet stars seems to be restricted to harmonic degrees less than 250 to 300. Well, we see some modes here seem to merge, but in between these modes which merge below some critical value of the harmonic degrees, there are modes which remain damped and which remain unpaired, and they also decrease with harmonic degree, and they form ultimately, if we go to L equals 0, they form the spectrum of normal modes. So we may consider this diagram for this diagram which we saw for L equals 0 for the spherically symmetric perturbations of Wolf-Rayet stars as a function of mass, to be generated by merging of modes with decreasing harmonic degree, forming strange modes. These are the lines here in this diagram which no longer depend or only weakly depend on the harmonic degree, and the normal modes with a steeper dependence on harmonic degree, which then ultimately form the spectrum of normal modes, normal modes in a sense, normal compared to strange modes, for the spectrum of radial perturbations. Okay, so the strange mode phenomenon as a result is not restricted to spherical geometry. It appears on all scales with harmonic degrees smaller than, say, 250 to 300, and we also have this nice complex conjugate symmetry for the strange mode. We have a pair of complex conjugate eigenfrequencies which are generated through the merging of two modes. Actually, we cannot predict which mode remains unpaired and which of these modes will pair. So this might be the subject for further investigation, for further research. Actually, in detail, we do not yet understand how these pairing and pairing occurs, and what causes the modes to pair and what causes the modes not to pair. Okay, so the result of this study then is maybe summarized. Well, to summarize, the additional modes come in almost complex conjugate pairs. The strange modes seem to be provided by pairing of normal modes and form complex conjugate pairs, and the strange modes and the instabilities are not restricted to radial perturbations, but they occur up to harmonic degree of about 250 to 300. Well, that demands, of course, a study or an interpretation, or we would like to get some deeper in understanding what causes this mode coupling, this mode merging, and why do these modes occur in complex conjugate pairs? What is the reason? That seems to be somewhat strange. And one tool to understand at least the complex conjugate symmetry in some cases is the so-called NAR approximation, which was developed in order to understand the properties of strange modes. So what does NAR means? NAR stands for non-adiabatic reversible. So what does this approximation mean, or what does this approach mean? Well, it is motivated in the first place by the observation that in these stars which are affected by strange modes, we have high luminosity to mass ratios which are reflected in a small ratio between thermal and dynamical timescale over a considerable fraction of the envelope. So that seems to be somehow related with a strange mode phenomenon. Thermal timescales are short compared to the dynamical timescales over a big range of the envelope considered. Okay, to discuss this NAR approximation, we consider the entropy. We have to do some thermodynamics. We consider the entropy as a function of pressure and temperature, so we take pressure and temperature as the thermodynamic basis. Then, as we have done often in this lecture series, we write down the differential of the entropy, and once we do it and write the entropy in terms of pressure and temperature, then we can write the differential of the entropy in terms of the relative differential of the temperature and the differential of the pressure. So ds is given by the specific heat at constant pressure times dt over T minus nabla adiabatic times dp by dp over p. This relation has been used and derived several times in the course of this lecture. So let us ask now, how can we make ds equal to 0? Well, an obvious, the change of entropy to be 0, well, an obvious way to make ds vanish, the change of the entropy vanish, is to ask or to require adiabatic changes of state. Adiabatic changes of state are characterized by the T over T being equal to nabla adiabatic over times dP over P. So the vanishing of this bracket corresponds to the adiabatic approximation, and ds can be made 0 by making this quantity or requiring this bracketed term to be 0. But there is also a second rather strange and well, not obvious way to get this ds equal to 0, namely by requiring that the Cp is equal to 0. So the question then is, if we can make this ds equal to 0, what does it mean if we make ds equal to 0 and the specific heat, or it's not really the specific heat, it is the heat capacity at constant pressure to be 0. Actually, this approximation requiring Cp equal to 0, or the heat capacity equal to 0, that is the content of the NAR approximation. Okay, the question of course is it meaningful? What are the results of these approximations? And what are the physical consequences and the physical implications of such a strange way of getting rid of the derivative of the entropy, or the change of the entropy? Well, the question is, where is this ds relevant in our perturbation equations? And obviously this ds, or ds by dt, the change of entropy with respect to time, appears in the energy conservation equation. So to write down the energy conservation equation for radial perturbations, for instance, L dash, the derivative of the luminosity perturbation, is given by, or written as, I sigma. This is the remaining, or this is the remaining of the time derivative of entropy with respect to time, because this term corresponds to the time derivative of the entropy. So this is given by I sigma, denoting the time derivative, times the coefficient C1 over nabla adiabatic times the bracketed term T minus nabla adiabatic P. So we can make this time derivative of the entropy 0 either by requiring adiabatic changes of state. This corresponds to the first possibility, or we can make it 0 by requiring that this term here, that means essentially the C1 is equal to 0. The C1 contains, of course, the specific heat, and it also contains the density. So this term actually can be made 0 by requiring low density or low heat capacity. It is not the specific heat which we set to 0, but it is the heat capacity, means the heat stored per volume. This is different from the specific heat by a factor of the density. So the NAR approximation then consists of not requiring this term to be 0, but requiring this term to be 0. Well, C1, this coefficient, was found to be proportional to the ratio of thermal and dynamical timescale, and well, C1 is smaller than unity if the thermal timescale is small for a large fraction of the envelope, and that actually seems to be consistent with our findings. Well, the findings for this star is that the ratio of thermal to dynamical timescale seems to be small over a large fraction of the envelope. And so the NAR approximation requiring this term to vanish seems to be consistent both with our findings and the C1 being smaller than unity, being proportional to this timescale ratio, is consistent with the NAR. So what we are doing, we find that in our models, this coefficient is in fact small. This is found simply by inspection of the run of the thermal and the dynamical timescale. And what we are doing now, we put it equal to 0. Small values are approximated, small values of C1 are approximated simply by setting C1 equal to 0. Okay, the effect will be the same as the adiabatic relation. The change of the entropy with time is 0 both in the adiabatic approximation and in the NAR approximation. Another quantity is also 0 here. Once the right-hand side is 0, the left-hand side is also 0. Well, it's clear in the adiabatic approximation we have no luminosity variation, but also in the NAR approximation the luminosity variations, the perturbations of luminosity must vanish. Okay, so to say, to compare these two approximations means, well, in the NAR approximation, ds by dt is 0 by vanishing heat capacity. C1 goes to 0, so ds by dt and ds is 0. Adiabatic means ds by dt or ds is 0 by t minus nabla adiabatic p by adiabatic changes of state, and this is enforced or given by C1 going to infinity. So we get the same result. ds is 0 once by having 0 thermal timescale and once by having infinite thermal timescale. So in both cases we are left with ds by dt, but for very different reasons. And in one case it implies a relation between pressure and temperature variation. In the other, it implies simply that this factor is 0. So what is the consequence? We've already talked about one consequence. Well, vanishing heat capacity means in principle we cannot do any thermodynamics anymore. Any thermodynamic relation, any thermodynamic statement requires a finite heat capacity. Without heat capacity we cannot do any thermodynamics. So the question is, what are we left with? Well, the thermodynamics cannot play any role, so we seem to be left by this approximation with a mechanical system. So we only keep the mechanics of the system. Well, an argument in favor of this is the timescales which we see for the strange modes. Of course, the frequencies operate, or the frequencies are associated with the mechanical timescale anyway, but we see that even the growth rates are in the dynamical regime. That it might be an indication that because also the imaginary parts are associated with the dynamical timescale, that we are actually dealing with a mechanical system. Okay, well, next consequence has already been discussed. The luminosity perturbation has to vanish since heat cannot be stored. If we have no heat capacity, we cannot store heat. A luminosity perturbation would require heat to be stored, at least for in an intermediate, not permanently, but for certain time interval, luminosity perturbation would require a heat capacity and heat to be stored for some time. Well, another consequence is once we do not have heat capacity, this means we can also not provide, or we cannot realize heat transfers between some elements. Heat transfer, for instance, from the internal heat of the star to mechanical energy of the perturbation. That means any instability mechanism which is related or based on a thermodynamic process like a Carnot type heat engine, this cannot happen, or this cannot work. So all instability mechanisms based on a Carnot type process, they can be excluded, and that means that kappa and epsilon mechanisms are excluded once we find the instabilities also within this NAR approximation. Then these cannot be caused by kappa and epsilon mechanism, because that would require thermodynamics, and this would require a finite heat capacity. So, okay. Well, and also the thermal and secular modes, which have been discussed in the beginning of strange mode research, they cannot exist because the I sigma term is now missing in our equations, and this is the only term which can be responsible for a spectrum of so-called secular and thermal modes. And finally, the last property is related to the name, non-adiabatic reversible. Well, if we now change time, or if we reverse the direction of time, that means we replace t by minus t, then the acceleration will, because of the square appearance of the time here, will not change. If we exchange t to minus t, then the acceleration will remain the same, and the only term which appears in the perturbation equation, which involves a time derivative, is the acceleration. So if this term is invariant with an exchange or with a transformation from t to minus t, or the reversal of the time direction. Well, and if you go to the perturbation equations and take, let's say you have a solution, and you take the complex conjugate of your solution and the complex conjugate of your equation, you see, because this I sigma term is now missing, then you see that with sigma also the complex conjugate of sigma should be a solution of the problem. Well, because we have only a quadratic appearance of the time here, we have only sigma squared, then with sigma also minus sigma squared. Minus sigma will be a solution. So once we have a solution, simply the symmetry of our equations guarantees that we have 4 solutions, namely with sigma also the complex conjugate, also the negative values minus sigma, and therefore also minus sigma, the complex conjugate of minus sigma is a solution of the problem. So the eigenfrequencies come in quartets of 4 solutions. In particular, once we have a solution, also its complex conjugate is a solution. This is pretty typical for mechanical system. It's no longer typical for thermodynamic system. Well, to rephrase the time reversibility, the invariance with a reversal of time, consider a solution, the time dependence of a solution, given as cosine sigma r times e to I sigma t, and reverse the time. Then the argument of cosine sigma r goes to cosine minus sigma rt, and the argument of the exponential goes with e to minus I sigma it. Once you reverse the time, well, cosine is symmetric, so cosine minus sigma r is equal to cosine sigma r, and here we have e to minus I sigma I, because we have, once we have sigma as a solution, also its complex conjugate is a solution. That means we have also in our manifold of solutions, we have also a term which goes to e to I, from e to I plus I sigma it, we have a solution which goes to e to minus I sigma I. So time reversibility is somehow connected, or time reversibility means that sigma and sigma and its complex conjugate is a solution, Or on the other hand, if sigma and its complex conjugate is a solution simultaneously, then this indicates that the system is time reversible. That's why this approximation is called non-adiabatic reversible approximation. And well, this time reversibility and the appearance of eigenvalues in complex conjugate pairs is typical for mechanical system. It's untypical for, it's not typical for thermodynamic systems. Okay, now we have considered this approximation, and of course we would like to know, at least for the Wolf-Rayet stars, what is the result if we perform, instead of the full non-adiabatic analysis, we perform an analysis where we artificially put the I sigma term equal to 0. That means in the energy conservation equation we artificially put this term to 0. So what is the result? We perform now an analysis exactly the same way, but without this I sigma term. This is then the NAR approximation for our star. Let's compare the result for the helium 0H main sequence models for spherically symmetric perturbations. Now this is the full result. This is the complete result, and the diagram on the bottom is the NAR result. You have to look very carefully to see any difference. Well, what seems to be lifted, or what seems to be done here, well, the thick dots denote an unstable mode, and because in the NAR approximation it means that we have always complex conjugate pairs. So each of these thick dots denotes both an unstable and its complex conjugate part. So these are, on these thick dots we have two modes, one stable, one damped mode, and its unstable counterparts. So, and here we have a small difference in frequency between the unstable and the stable counterparts of these almost complex conjugate pairs. So this means it gets exactly now the same frequency. The ordinary modes, the normal modes, are seem to be not affected by this approximation, and even the strange modes are not affected very much by this approximation. So for Wolf-Rayet stars, we deduce from this experiment that the NAR approximation for Wolf-Rayet stars is even quantitatively not bad. Let's compare the imaginary parts in the upper diagram. Well, these are the damping rates of the normal modes. Well, we expect them to collapse to 0 because if they wouldn't collapse to 0, they would have to produce a complex conjugate pair instead. But all these normal modes, in fact, they collapse to 0 imaginary part, and now this pair of complex conjugate modes becomes exactly complex conjugate, whereas in the full problem it's only approximately complex conjugate, and we are left with much nicer diagram. All modes have now, all ordinary modes have 0 damping rates, and the complex conjugate pairs are pretty similar to the unrestricted, not approximated full non-adiabatic problem. So this approximation, even if it sounds a little bit strange, putting the heat capacity equal to 0, it provides, concerning the stability analysis, even in the quantitative sense, it provides very good approximation. Okay? So it doesn't seem to be that bad to adopt this approximation. So we are left with the following result. For Wolf-Rayet stars, the NAR approximation gives even quantitatively satisfactory results. Well, we can do the same for the hydrogen-deficient carbon star models. Well, if we do also the NAR approximation, well, we again see this trace of mode 1. The mode 1 is still there. Also, the mode 5 is there with an extremely high growth rate. But now we see some staircase behavior for the high frequency modes in the NAR approximations, and it's a pity that you don't see what happens here, but it looks a little bit different from just a mode passing through the other sets of ordinary modes. Once we have a crossing of these modes, then they seem to have appeared in the following way, or they seem to form in the following way. So these are two crossing modes, and once we look for the imaginary part, it forms such bubbles. So it seems that the full non-adiabatic problem of the extreme hydrogen deficient star is some phenomenon which passes here, which forms very strange coupling or merging and demerging of modes, which is associated with bubbles of complex conjugate pairs. And these bubbles, once we somehow smear out these bubbles, then we arrive at the full non-adiabatic problem. So keep this in mind, and if you smear out these instabilities or the negative values of the growth rates here and compare it to the full problem, let's go back to the extreme hydrogen deficient carbon stars. Let's look for the modal diagram. Well, these are the imaginary parts. So you see these maxima seem to be reminiscent of these bubbles which are now merged or smeared out, whereas in the real part you still see the trace or some trace of this mode running through. In the NAR approximation it looks a little bit different, but at least the trace of this mode is also seen in the NAR approximation, and moreover the value of the value of sigma I is comparable. This value found in the full problem is comparable to the value of the instability or the growth rates in the NAR approximation. So the NAR approximation at least provides some approximation also to the unstable mode, and that, of course, we are mainly interested in the unstable modes and possibly in the instability mechanism which is behind these modes. Okay, also in the case of the hydrogen deficient carbon stars, this approximation seems to provide an approximation which is even quantitatively not too bad. Okay, so well, all these phenomena, all what we have talked about now, is or seems to be associated with the crossing of modes. If we go to the Wolf-Rayet stars, well, we see that the strange modes are either formed by merging of modes, by, so to say, by coupling of modes, and then subsequently by the crossings of two sets of modes. So the coupling or the crossing or the interference or the resonance of modes seems to be, in this phenomenon, seems to play a basic role. This might be the motivation to study or to deal with mode coupling in detail. And that's what we want to do now. So we consider the coupling or the resonance or the interference of two sets or of two modes. So the observed crossing of modes will gives rise to an investigation of mode coupling. So consider two configurations or two sets of modes which interact with each other. So we have considered two systems or two subsystems which formally might be described by two independent dispersion relations. So you have one set of modes, which is one set of modes, for instance, which depend on a parameter. So you have sigma r as a function of parameter. Let the parameter, for instance, be the mass. Then we have a set of modes which have almost no dependence on the parameter m. This is one set of modes. Let's call, or let them be described by a dispersion relation d1 of omega equal to 0. So this is the set 1 described by a dispersion relation d1 of omega. Then let's consider a second set of modes. This is set 2, and the set 2 should be described by an independent dispersion relation d1 of omega equal to 0. Well, the first dispersion relation will have solutions omega 1, and the second set will have solutions omega 2. So these here are the omega 1s, and these here are the omega 2s. Well, and we have crossings between these two sets of modes, and the crossing, if they are independent, of course, then these two dispersion relations have to be satisfied separately. Now, if we admit some coupling between these two sets of modes, then we can describe the coupling simply by the product of these two dispersion relations not being 0, but being equal to some coupling functions epsilon of omega. Epsilon may depend on omega itself, and epsilon should describe a small, possibly a small coupling between these two sets of modes. So if epsilon is 0, then we arrive for the solution of the system. If no coupling exists, we have d1 of omega equals 0 and d2 of omega equals 0 as the separate dispersion relations. Now, if epsilon is not 0 and we have a small coupling, well, if d2 is not 0, then we can write d1 of omega as epsilon over d2, and once d2 is not 0, then this will be small, and d1 of omega equal to 0 will be the solution of the problem. Once the same is true for d2, if d1 is not 0, then d2 equal to 0 will be a solution of for determining the eigenfrequencies omega 1 and omega 2. This happens that omega d2 is not 0 and d1 is 0. D1 equals 0 gives the dispersion relation or determines the roots of this equation. Is required is that these two d1 and d2 are not 0 at the same time. So the requirement is that d1 and d2 are not 0 at the same time. This means that they have a common root or that the modes cross. So apart from the mode crossings, these are these points here, we have the original dispersion relations, we have the unperturbed or the uncoupled dispersion relations, and we have the uncoupled mode. Modes only close to these crossings we have to take into account the coupling of these two dispersion relations described by epsilon of omega. Okay, so apart from the crossings, or we have the original modes, but close to the crossings, we have to take into account the coupling between the two sets of dispersion, sets of modes described by the dispersion relation D1 and D2. So if D1 and D2 are simultaneously zero, that means if omega 2 is equal to omega 1 is equal to omega 2, that means at a mode crossing, we have to consider what happens due to the coupling. Now we describe the difference of the original frequencies omega 1 and omega 2 by small delta, and we describe the difference of the final frequency omega with compared to omega 1 with capital delta. According to these definitions, we may write omega as omega 1 plus delta, which is expressed in terms of omega 2 equal to omega 2 plus, because omega 1 is delta plus omega 2, so this is omega 2 plus small delta plus capital delta. And we have to solve the dispersion relation D1 at omega might be expressed in terms of omega 1 plus capital delta times D2, which might of omega, which might be expressed as omega 2 plus delta, small delta plus capital delta equal to epsilon. Okay, what we are doing is we expand these dispersion relations around omega 1 and around omega 2. Then we have that this dispersion relation or this function in an expansion may be expressed by d1 at the point omega 1 plus the derivative of d1 with respect to omega times delta, and the similar process here for the dispersion relation d2 is d2 of omega 2 plus delta times the derivative of dispersion relation 2 with respect to omega is equal to epsilon. Now d1 of omega 1 and d2 of omega 2 is 0 simultaneously because we are expanding around a crossing of two modes. Then we are left with a quadratic equation for delta, measuring the difference between the final value of the frequency and omega 1. Delta times delta plus small delta plus capital delta is equal to epsilon divided by the derivatives of the original dispersion relations d1 and d2 with respect to omega. Well, this is a quadratic equation, and we can easily solve this quadratic equation. Solution of the quadratic equation gives capital delta is minus 1/2 the difference of the original eigenfrequency, uncoupled eigenfrequencies, plus the square root of delta squared plus epsilon divided by the derivatives of the dispersion relations. If delta is large, if the difference of omega 1 and omega 2 is large, that means we are far away from the crossings, delta large, then we can neglect this term compared to delta squared. So we are far off the crossing. Omega 1 delta is omega 1 minus omega 2, and this means omega 1 delta big means we are far away from the crossing. Then we can neglect this coupling term, and delta is either 0 or minus delta, and this means, according to the definition, that delta is omega minus omega 1. We have omega equal to omega 1 and omega 2. So we arrive at the decoupled value. What happens at the crossing if delta is small, or delta might be neglected with respect to this epsilon term? then we have omega, delta is omega 1 minus omega 2. So omega is omega 1 plus minus, taking the definition of capital delta, plus minus the square root of this coupling term, which is given in terms of epsilon, the coupling between the two dispersion relations, divided by the derivatives of the dispersion relations. Okay? Now let's assume for simplicity that omega 1 and omega 2 are real frequencies. How does this look like? Okay, if d1 by the omega and d2 by the omega are real, omega 1 and omega 2 are real, and epsilon is a real quantity, well, then in the case that the term underneath the root is positive, we arrive at the following coupling picture. The dashed lines are the omega 1 and omega 2, which cross at, or which are in resonance at some position, depending on the parameter. So what we get in this case, when this term is positive and the root here is real, then we get the following picture. Omega 1 is now, or the previous omega 1 is now connected continuously to omega 2, and omega 2 is now connected continuously to omega 1. This is called the coupling according to the avoided crossing scheme, because the crossing is avoided and then the frequencies avoid each other simply by connecting omega 2 to omega 1 and omega 1 to omega 2 and vice versa. Okay, now let's consider that the term underneath the root here, the argument of the root is negative. Then this, of course, this gives this provides a complex conjugate pair of solutions. So how are the functions connected now? These are the original uncoupled values omega 2 and omega 1. Now they couple in a way, it's just the properties of this root. They have a common, they are now connected. Omega 1 again connects to omega 2, and omega 2 connects to omega 1. And once at the point of where this relation gets a vertical tangent, these modes seem to merge in that sense, and they have a common real part. This is when this root comes into play. There is one common real part, but two complex conjugate imaginary parts. And once we plot the imaginary part here, then we have a bubble or an instability band or a bubble of instability between those places where these modes have merged to give a complex conjugate pair. Okay? It's simply discussing the properties of this quadratic equation. So we have in principle two ways how modes can couple, or two ways in which a mode crossing may unfold. It's either the avoided crossing scheme or it is the instability band scheme. Now let's go back to our extreme hydrogen deficient carbon stars. Well, these guys remind you of bubbles of instability, and here, these guys over there, they remind you of avoided crossings. And if the picture of if the graph would have higher quality, you would also see that you find exactly the coupling scheme which we have described in the last picture. So what you see here, I will draw it here on the blackboard shortly. So we have a set of normal modes which are crossed by an additional mode. This is the uncoupled system. Now in the upper part it seems that we have coupling according to the avoided crossing schemes. In other words, the coupling constant here, the coupling epsilon, is positive. So we connect it in that way. So this is connected to this way, in that way, and here we have connection according to that way. This is an avoided crossing. Here, let's do another avoided crossing. So they are connected that way, and these are connected this way. So this gives this staircase impression, and these are the modes seen here. So this is the trace of an additional mode which has passed through the set of normal modes. Now let's change the coupling scheme. Let's change it to instability bands. Then it will have to be connected that way, this way here, and we have a common real part here. The next one also giving this coupling scheme. Then we have that way, and we have a sequence of instability bands or instability bubbles. And in the imaginary part, we have a complex conjugate bubble here. And well, let's do it there. This is a complex conjugate bubble here, and a complex conjugate bubble here. So using that coupling scheme, or having in mind the coupling scheme which we have discussed in the last few minutes, we can now explain or interpret this diagram simply by one mode crossing these the normal modes and coupling either according to the avoided crossing scheme or according to the instability band scheme. So the consideration of the general possibilities of mode coupling helps in some sense to interpret this diagram and to understand at least partially this diagram. So it's a tool for getting some order in modal diagrams and to interpret them in terms of crossings of different kinds. Okay, because this is a little bit counterintuitive, let's give some examples for mode coupling, which you probably already know, but you are probably not aware of the fact that mode coupling is present in these cases. Well, first case is the so-called double pendulum. The double pendulum consisting of two pendula acting under the action of gravity and a coupling spring which have different length. Okay, this is the situation. We have two pendula which have different length, one with the length L and the other one the length capital L, two masses, and which are coupled through a spring with constant d and gravity acting in the vertical direction. You probably know this problem from basic physics. Well, how many modes does this system have? We have two systems, and obviously we are talking about mode coupling. So how many modes does this system have? Infinitely many. Well, two pendula, two modes. So, and we are considering now a system with two modes and the crossing of these two modes, which can be done completely in an analytical way. Okay, so let's consider the equations of motion for this pendulum. Well, you probably should be familiar with that. Well, the forces which act on the pendula are either gravity and the spring. The force exerted by the spring. Well, the gravity, so to say, the horizontal component of the gravity is gravitational force is mass times the gravitational acceleration, and the component in the direction of x, this is the motion of our in a certain approximation, the motion along which our pendulum move. So x1 will be the displacement of pendulum 1, and x2 is the displacement of pendulum 2. So we are left with it. The gravity is, the horizontal component of gravity is x1 over the length, and for the pendulum 2 it's x2 over capital L. This is the component of the gravity parallel in the horizontal direction, or parallel to the displacement of the pendulum. The spring is the force exerted by the spring is spring constant times the difference of the displacements of x1 and x2. Well, a corresponding formula for the gravity and the spring of pendulum 2. The spring, the force exerted by the spring, is just the opposite, because actio equal to reactio, it has to point in the opposite direction. The gravity is analogous to the gravity of the first pendulum. So these are the forces acting on our pendula, and according to that we have the equation of motion. Mass times acceleration of pendulum 1 is given by gravitational force in the horizontal direction acting on pendulum x1 plus the force exerted by the spring. The opposite sign here for the second pendulum. Now, rearranging these two equations of motions, we are left with a system of two differential equations with respect to time, where we have x, the acceleration given by the gravitational forces, and the spring forces. Now, this is an equation, a linear equation with constant coefficients. Linear equation with constant coefficient have as a solution exponential of time. This time derivative will give a minus omega squared instead of the second time derivatives here. And we are then left with two equations for x1 and x2, the displacements x1 and x2 for the two pendula. Well, this is a homogeneous linear system with respect to the displacement x1 and x2, and might be written matrix as a matrix times the vector x1, x2, and this has a solution only once the determinant of A is 0. So the condition for the solvability of the system is minus omega squared plus g over L, this is the first bracket, times the second bracket, minus the diagonal terms minus d over m squared is 0. Or we rearrange it in the following way: omega squared minus omega 1 squared times omega squared minus omega 2 squared is equal to d over m squared, which we identified with a coupling of the two systems epsilon, which is in this case bigger than 0. So omega 1 squared is simply an abbreviation for g over L plus d over m. This is the first, so this might be denoted by omega 1 squared, and we have omega 2 squared as an abbreviation for this term. So if epsilon is small, or the coupling is small, or in other words the spring is weak, then we have two independent frequencies, omega 1 and omega 2, determined by the vanishing of the first bracket and the second bracket respectively. We can also write down an exact solution, because this is a quadratic equation for the omega squareds, and we can write down the exact solution in that case. So the exact solution is given by this, the solution of the quadratic equations. So once the difference of the unperturbed or the uncoupled frequencies is big, that means this term is bigger than epsilon, then we get as a solution of the full problem, as an exact solution, omega 1 squared and omega 2 squared. This is no longer true if epsilon is no longer small compared to the difference of the uncoupled frequencies. In that case, we get omega squared is the mean, or is the average of omega 1 squared and omega 2 squared plus minus square root of epsilon, and epsilon was simply the square d over m squared. So this is given then omega squared is the mean of these two plus minus d over m. Once we apply the mode coupling formalism to this system, we arrive at d1 of omega squared times d2 of omega squared is equal to epsilon. The d1 is omega squared minus omega 1 squared, and this similar relation for d2. The epsilon is d over m squared. So we have two dispersion relations, and we have a coupling between these two, and we can apply the coupling formalism. Then the d1 over d2, the d1 over d omega squared, which is required for the coupling mechanism, is 1, and similar d2 by the omega squared is 1, and we get, if delta is large, if the difference of the omega 1 and omega 2 is big, then we get as the capital delta 0 and minus delta, and we get the decoupled values, meaning omega squared is omega 1 squared and omega 2 squared. If delta is small, then the coupling epsilon is significant, and we are left with omega squared equal omega squared is omega 1 squared plus the root describing the coupling. This is omega 1 squared plus minus square root of epsilon, and this is omega 1 squared plus minus d over m. Okay, and if you compare it with the exact result, well, then it is the mean of omega 1 and omega 2. If we are at a position where omega 1 is equal to omega 2, this is omega 1 squared plus minus d over m. So it's exactly the same result. So what does it mean if we try to illustrate this in a graphic way? So let's write down, or let's illustrate this behavior of these two modes. We have two modes corresponding to the two pendula. Then omega will be a function of the length L, small l, whereas we take, in our experiment, we take the length of one of these pendula equal to constant. So we take the pendulum 2 with length capital L, we take this constant, and we will have omega 2 constant as a function of the length of the pendulum 1, which changes according, which is in the experiment taken to change. So omega 1 goes essentially like 1 over L plus some correction due to the spring constant. And what happens now, and this can be explicitly seen either in the exact solution or in the coupling formalism. Now the omega 1 is now connected continuously to omega 2, and omega 2 is connected continuously to the omega 1. And the separation of these two frequencies is exactly delta and controlled by the coupling or by the spring constant. If we artificially would have the case, which is not exactly the case here for the double pendulum, that epsilon is smaller than 0, if, for instance, the spring constant would be imaginary, what that means is not clear. So if artificially epsilon would be smaller than 0, then they would couple in the way that here we have a common real part. Again, omega 2 is connected to omega 1, and omega 2 is connected to omega 1 here. We have a common real part, but we have a bubble of instability around the coupling of these two modes. So this would be the case if we artificially switch to a negative value of the coupling. So we have an avoided crossing. The avoided crossing is realized in this system of the coupled pendulum. Probably you have never come across the fact that your double pendulum, which you consider in lab courses or so, that this involves the coupling scheme of two modes according to avoided crossing. And if you artificially change to epsilon smaller than 0, you could even produce, in this simple system, could even produce an unstable situation where you produce an instability bubble by the coupling of two modes realized here with the double pendulum. Okay, this afternoon I think we have run out of time. This afternoon we'll consider another problem, which then brings us back to astrophysics and how a simple system which intuitively, by which we can intuitively interpret the modal diagrams of a star and understand what's going on there. Okay, thanks very much for this morning, and we will continue at this point in the afternoon. this morning we have studied highly non-adiabatic stars, and we encountered the phenomenon of strange modes and strange mode instabilities being extremely strong instabilities operating on the dynamical timescales, and associated with the strange modes and the strange mode phenomenon is the occurrence of mode crossings and mode interactions. We have then considered or investigated the general property of a mode crossing and the general behavior around mode crossings, and we finally have given a analytically treatable example which has only two modes and where two modes interact and provide a mode crossing which can be treated entirely in terms of analytical computations. This was the double pendulum, and as an example we have found that in fact the well-known and known to everybody the situation or the configuration of the double pendulum might be explained or interpreted in terms of a mode crossing which has unfolded into an avoided crossing. If artificially the coupling constant could be set to a negative value, then we could have obtained an instability band. Now let us go to another example of mode crossings, of multiple mode crossings, and we will consider for this purpose the subdivided organ pipe. Organ pipe was always the analogon to our stellar configuration, and we could draw many parallels between the organ pipe and the stellar configuration. This example will provide or will allow for multiple mode crossings, and the picture we develop from this subdivided organ pipe will be very helpful in the subsequent chapters of this lecture to understand the modal structure of a strange mode unstable and a strange mode affected star. So let us consider the subdivided organ pipe first. What is it? Well, it is an organ pipe. The example, can we take it a little bit smaller? Okay, that's fine. So we have an organ pipe of length L, and we have a diaphragm in this organ pipe which subdivides the organ pipe in two pieces, into a bottom part and an upper part, and this diaphragm lies at a distance L from the bottom of the pipe, and it might be shifted up and down. In the experiment we will shift it from the bottom to the top, and we will see how the acoustic spectrum of the organ pipe will change then. Okay, if this diaphragm is, well, of course the organ pipe satisfied the one-dimensional acoustic wave equation. We have already considered this in detail, and the acoustic wave equation which is valid for this configuration is second derivative with respect to time of the velocity perturbation, the Eulerian velocity perturbation, minus sound squared times the second derivative of the velocity perturbation with respect to the spatial coordinate is 0. Now we have at least two boundary conditions at the bottom and the top of the pipe. This is if we have rigid boundaries, or if the organ pipe is closed on both sides, then we have to require that the velocity perturbation has to be 0 both at the bottom and the top of the pipe. That means at x equal to 0 and x equal to capital L. If the diaphragm perfectly decouples the upper and the bottom part of the pipe, then we have to apply this boundary condition also at the diaphragm. If it's a perfect decoupling of the two parts, then we have to imply these boundary conditions for the bottom part also at x equal to L, and for the upper part at x equal capital L. Of course, the two previous boundary conditions still have to be satisfied. So we generate two spectra in principle, one associated with the bottom part of the pipe and one with the upper part, and this is generated by requiring the boundary condition at x equal to 0 and x equal to L at the position of the diaphragm, and for the upper part at the position of the diaphragm and at the upper end of the pipe. Okay, so these two parts, these two spectra, which are generated by imposing the boundary conditions in the way given here, they are, if the diaphragm is perfect, they are independent of each other. So the two parts of the pipe cannot communicate. The solution of the wave equation in any case is given by an exponential I omega t plus ikx. So we have an exponential behavior both with respect to the time behavior and the spatial dependence. The dispersion relation which we obtain from this form of the solution, if we insert it into the one-dimensional wave equation, is identical for the upper and the lower part, and it's given by minus omega squared, eigenfrequency squared, plus c sound squared times wave number squared is 0. Now we impose, with this dispersion relation valid in both parts of the pipe, we impose boundary conditions for the bottom part. These read in the following. So this is the form of the perturbation. The velocity perturbation is a superposition of a wave which goes from bottom to top and from top to bottom. So at x equal to 0, we derive 0 has to be c1 plus c2, and at x equal small l we have 0 is c1 times e to ikl plus c2 e to minus ikl. Replacing c1 by c2, and we are left ultimately with 0 is e to ikl minus e to minus ikl, and in the end we have the following relation for, or the following equation determining the wave number k. E to ikl is 1, and 1 might be written in the complex plane as e to I times 2 pi n, where n counts the number or the order of the overtone. N equals 0 is a fundamental, n equals 1 the first overtone, and so on. So k is given by the order of the mode divided by the length of the bottom part of the pipe, and omega squared is then given according to the dispersion relation simply by sound speed squared times pi squared times the order squared of the mode divided by the length or the distance between the bottom of the pipe and the position of the diaphragm. Well, let's consider now the spectrum of the upper part. Well, there we have to impose the boundary condition at the position of the diaphragm. So velocity is 0 there, which is given by c1 times e to ikl plus c1 to e to minus ikl, and the boundary conditions at the top of the pipe or of the top of the upper part has to be imposed at the position capital L. This gives two boundary conditions, and this equation leads to a linear homogeneous equations for C1 and C2, may be written as a matrix A times the vector C1 C2. This has to be 0, and the necessary condition for this to have a non-trivial solution is that the determinant of the matrix A has to be 0. The determinant of this matrix is simply these two elements minus these two, the product of these two elements. So the determinant is given by e to ik difference between the position of the diaphragm and the length of the pipe minus e to ik, and again the difference between the position of the top of the pipe and the position of the diaphragm. This again leads to a similar equation as for the bottom part. That should be expected that the relations are similar, but e to ik L difference L small l minus capital L is 1. This is again in complex analysis given by e to I 2pn times the number or the order of the mode now for the upper part. This is a different n from before, so this is the order of the modes of the upper part, and so k, the wave numbers for the upper part of the pipe, of the top part of the pipe, is given by pi times the number, the order of the mode times the difference of the position of the diaphragm and the length of the pipe. Accordingly, with the dispersion relation, we end up with omega squared is c sound squared divided by L minus capital L squared times essentially the order of the mode of the upper mode squared. So these are the two spectra of the bottom part and the top part. U means upper part and B, subscript B, means the bottom part of our pipe. Okay, so we have two dispersion relations, the bottom part and the upper part, and the dispersion relations are given by omega squared minus c sound squared over L squared times pi squared times the number, the order of the mode, respectively, for the upper and the bottom part. Well, these are separate dispersion relations once the diaphragm is perfect and the modes do not have the sound waves of the upper and bottom part, do not have the chance to interact with each other. In general, however, the diaphragm is not perfect and we will have a coupling between the upper and the bottom part of the pipe. So to account for the imperfectness of the diaphragm, we write the dispersion relation of the complete system containing both the upper and the bottom part as a product of the dispersion relation for upper and bottom part being no longer zero but being given by a coupling function epsilon, which may depend also on the frequency omega. We will assume in the following that epsilon is bigger than 0 and that epsilon is a real quantity. Just for simplicity, we could also assume epsilon complex or negative. If we want to calculate this epsilon, we have to go in a more sophisticated way. Well, but it could be done. I will not do it because it is easy and it's straightforward to do it, but it becomes the mathematics in the algebra explodes. So you will have you will have to deal with many terms, and actually for the physical insight it does not provide a big advantage. And so I just sketch a little bit in a very rough way what could be done, or how a more sophisticated treatment of this system might be done. Well, we can, in a sophisticated treatment, we may regard the diaphragm as a thin slice with high sound speed. We just take a thin slice which has a high sound speed compared to the sound speed within the upper and bottom part of our organ pipe. Well, the acoustic wave equation is similarly valid in this within this slice as in the pipe as well. So there is no change concerning the wave equation that needs to be considered. It's only that the sound speed has a different value within this slice than outside in the organ pipe. Well, the boundary conditions that have to be imposed are the same as before. The velocity perturbations have to be 0 at the bottom and the top of the pipe, and at the boundaries of the slice. However, just we have to impose continuity equations, because the wave equation is of second order with respect to the differentiation with respect to the spatial coordinate. In order to allow for a second order derivative, of course, the first derivative and the function v tilde itself have to be continuous. So at the boundaries, at the edges of the slice, at the interfaces of the slice, the velocity perturbation and its derivative with respect to x have to be continuous. And these continuity equations then, well, the continuity equation, the continuity conditions will then allow for a continuous connection of the two different parts of the pipe. And finally, what you end up with is an explicit form of the coupling constant or the coupling function epsilon. Okay, well, once you go through the analysis of this problem, you will find similarities to a well-known problem, a problem which is well known to you. It is the problem of the tunnel effect at a potential barrier. So in that case, you also adopt continuity conditions at the edges of the potential barrier, and what you will find is some kind of tunneling, now not of quantum mechanic waves, but of acoustic waves through an acoustic barrier which is caused by a slice with higher sound speed, with high sound speed. So the mathematical problem is very similar to the effect of the tunnel effect at a potential barrier in quantum mechanics, and the final result then is some kind of the probability for tunneling, or here it is not the probability for tunneling, but the function which describes the coupling of the top and the bottom part of our organ pipe. Okay, the final result is epsilon as a function of omega, which is bigger than 0 and is real. Well, since epsilon is bigger than 0, these mode crossings are expected, or any mode crossing is expected to unfold into an avoided crossing. No instabilities and no instability bubbles are generated in this way. Okay, so well, we will now do an experiment. We change the position of the diaphragm from bottom to top. So we change the length of the bottom part from 0 to capital L, and at the same time we reduce the length of the top part of the pipe from capital L to 0. So we have, and we consider now what the frequencies, how the frequencies of the top and bottom part vary with the position of our diaphragm. We will do it not mathematically, not in explicit doing explicit mathematical computations. We do it in a more intuitive way, an intuitive graphical way. We'll see in a moment how we shall proceed. So the experiment will be shift diaphragm from bottom to top, and assume that the modes couple with a finite epsilon, so the diaphragm is not perfect. Okay, so what we have for the bottom part, we have a 1 over L dependence of the frequencies. So once the diaphragm is at the bottom, the frequency of the bottom part are infinite. So they tend to infinity if we decrease the length, the position of the diaphragm to 0. They are at infinity, whereas the frequencies of the upper part are regularly spaced, and they have a fundamental frequency and accumulate at infinity. Now, well, once we shift it now from the position from the bottom to top, then the frequencies of the bottom part will decrease like 1 over L, and finally once we arrive at L equal capital L, we have a we have a spectrum having a fundamental, first overtone, and so on. What happens to the upper part? Well, if we change from capital L from L equals 0 to capital L to the top, well, then the frequencies which have been at L equals 0 been finite and regularly spaced will diverge like 1 over L minus capital L once we approach the top part of the once we approach the top of the pipe, and the length of the upper part goes to 0. So then the frequencies of the upper part of the pipe will diverge. So these ones decrease with L, the other ones increase with L. So it is inevitable that these modes will cross. So here again omega, and here is we plot omega against the position of the diaphragm. Here is capital L and here is 0. So for the bottom part we have infinite frequencies here, and they decrease once we approach L. So this is the fundamental, first overtone, second, and so on. They diverge for the position small l going to 0. The other just do the opposite. They start here, the upper part starts here, fundamental, first, second overtone, and it increases and diverges once we approach capital L. So we get this picture, and we inevitably get multiple mode crossings between the upper and bottom parts of our pipe. So we have generated an infinite set of mode crossings which do not stay as they are. This would be the picture if the two parts of the pipe would be completely independent and the diaphragm would be perfect. Actually, this picture must be symmetric with respect to L capital L halves, so we have a symmetric picture with respect to this line, which is L half. Okay? Everybody agrees, or objections against this picture? Okay. Now we know if the diaphragm is not perfect and epsilon is bigger than 0, then these crossings cannot stay as they are, but they have to unfold according to the avoided crossing scheme. So let's take one of these crossings, for instance here. This is the crossing. Avoided crossing means that this mode is continuously connected to that one, and this one is continuously connected to that one. The same happens here, and we get, as a result, we get an avoided crossing here. So this gives the impression of a staircase of modes, and it gives a rather bewildering and at first sight not understandable pattern of the crossing or of the run of the modes as a function of position of the diaphragm. I've done this here a little bit more in detail and more careful. So this here is the modal diagram which we expect. Well, the black lines are the decoupled, the original modes, the bottom modes. This is a set of bottom modes decreasing with increasing L. These ones are the spectrum of the modes in the upper part of the organ pipe, and the crossings here have unfolded according to the avoided crossing scheme, and so this gives this wave-like appearance for the run of the various modes as a function of position of the diaphragm. If we artificially would be able to have a negative coupling or have negative values of epsilon, then we would have a coupling in the green scheme. So then these modes would be connected, and we have a common real part in between these couplings. The same would be here, but at the same time we would have a bubble of instability, and the imaginary part then would no longer be zero. So we may have, if the system would allow both for negative and positive coupling, then we would have avoided crossings or instability bands within the same system. It depends on the sign of the coupling whether we get instability bands or avoided crossings. Maybe we can use, or we keep this picture in mind without the negative coupling, without the instability bubbles. Just keep this picture in mind. Maybe we can make use of it later on once we consider the modal diagram of a massive star. So I'll come back to this point, and of course if we find a massive star which shows a modal diagram which is similar to that, then we might ask, well, there must be somewhere, there must be in this star, must be a diaphragm, like in our organ pipe. Question is, where is this diaphragm and what makes this diaphragm? And if this is true, then we can, keeping in mind the simple picture of the subdivided organ pipe, we may get a feeling and an interpretation of the modal diagram of a massive star. I have done this in detail because you actually can use it, and you can transfer this picture to the modal diagram of a massive star and interpret the diagram in using this simple picture of the subdivided organ pipe. Well, the advantage of this picture is you can draw the modal, the run of the modes without reference to any complicated mathematics. It's just the coupling scheme which you need to know, and the run of two sets of modes which might be caused or might be generated by having a acoustic diaphragm in your star, which in the course of evolution may shift from bottom to top of the organ pipe. Okay? Questions?
So how do we determine what instability will be at the center, like L by 2 part, and the bottom is?
Yes. You mean here?
How do we determine that there won't be any double instability in this without
Well, the red curves assume that epsilon is positive. And this is artificially assuming or assuming that we have a negative epsilon, then we would unfold it according to that scheme. Actually, epsilon is positive for the organ pipe. It's just as a, well, it's an academic question. How would the diagram look like if we would have the possibility to have negative coupling? How would the picture look like? Actually, it will not look like, because we know epsilon is positive, so we will only have avoided crossings. Sequence of infinitely many avoided crossings. So it's the hypothesis that we might have epsilon smaller than 0. Okay? Well, now, well, the occurrence of mode coupling and the occurrence of instability bubbles is not restricted to stars and strange mode. They they occur also in many ways in fluid mechanics. And one of the examples, one of the nicest examples I know of, is the stability problem of plane Couette flow. What is plane Couette flow? Plane Couette flow is the flow between two planes which are sheared along each other. In a viscous treatment, then a shear layer will develop where the velocities are at the boundaries are equal to the velocities of the boundaries, and this shear flow is generated simply by the motion of the two planes shearing along each other. So the surfaces are, these two surfaces are shearing and generating a shear flow between the two confining planes. Well, for this flow it's found that turbulence sets in around a Reynolds number of thousands, and if we do a stability analysis, then we will find that actually if the theory is incompressible, then we will find that laminar flow is always stable, and people therefore think that there is a subcritical transition to turbulence. Well, we can also consider compressible perturbations, and if we do that, then we find in fact instabilities in the supersonic regime, and the critical Reynolds numbers are of the order of 100, and these instabilities in the supersonic regime are produced by resonances or mode crossings among sound waves. And I will show you the picture. So we have a nice example in that case for the instability bubble picture, or the instability bubble picture, which is usually not seen in these very simple case in the double organ pipe. In the subdivided organ pipe we always have avoided crossing, and also for the double pendulum we have only avoided crossings. Here we have the case where we have crossings of modes which have unfolded into bubbles of instabilities. So what is going on there? What is plotted here is the pattern speed of waves which have a character of standing waves between perpendicular to the planes, but which have the character of waves traveling along or in the flow direction in x direction. So these are modes. These are a set of discrete modes. This mode goes in the positive x direction, and those with negative values go in the negative x direction. So we have two sets of modes with standing character perpendicular to the planes and with traveling character along the parallel to the planes, and we have two types of waves going in opposite direction. The system should be symmetric with respect to plus and minus x. These are the modes, and once we turn on now our flow, and the flow speed is parameterized or given here in terms of the Mach number measured at the edge of the flow. So this so the flow speed is 0 here, and it increases, and the flow speed is measured in units of the sound speed. So we plot it here as a function of the Mach number. So what happens here is these modes are affected by the flow, that they are traveling parallel or anti-parallel to the flow, so they are affected and they become distorted, and they become distorted in a way such that they cross each other. So this is a plot where where we succeeded in decoupling these two sets of modes. So they are here neutrally stable, and they're decoupled. We could suppress the coupling between these, but once we turn on now the full system of equations, then we will see how these mode crossings have decoupled. So it now looks like the real part looks like kitchen tiles here. They are merging around these crossings. Then they form the typical instability bubble coupling, and they decouple again here. So we have lots of overlapping resonances and couplings in this kitchen tile profile. The imaginary parts look like these. These are the bubbles which correspond to all these parts here. So we have a superposition of many bubbles, and this is typical instability bubble result of the coupling or of the crossing of two modes having unfolded, this time not according to the avoided crossing scheme, but according to the instability band scheme. Actually, we have also some avoided crossings here, which are the outermost crossings, which have unfolded into avoided crossings. So we have also a sequence of avoided crossings here, but the main part of the crossings have unfolded according to the instability bubble scheme. So just to show you a very clean case of coupling, or very clean case of coupling which has unfolded into the instability band scheme. If you remember the coupling which was found in the hydrogen deficient carbon star, it was simply a sequence which is similar to one of these sequences found here. So it's one instability bubble behind the next one. Okay, now, well, we have seen fluid mechanics. In fluid mechanics we have many examples, compressible Couette flow, examples for mode coupling and instabilities associated with mode crossings and mode couplings. We have the hydrogen deficient carbon stars, and we have the Wolf-Rayet stars, which may be regarded as one-sided instability bands. So what we see is the beginning of a coupling scheme. We don't see the end of the instability bubble, we see just the onset of the instability. Well, this scheme, the general coupling scheme, may be used to decompose the system, or to decompose the modal diagrams into the constituent modes and reduce the complexity of spectra. It may also be used to find missing modes, and occasionally these coupling schemes may contribute to a better understanding of the instability mechanism. Now, well, we are dealing with strange modes, and let's now come back to the study of strange modes and non-adiabatic stars. Well, the Wolf-Rayet stars and the hydrogen deficient carbon stars are by no means the only stars where strange modes and associated instabilities are found. If you go to massive stars with high luminosity to mass ratios, you inevitably see strange modes and associated instabilities. So for instance, if we go to massive stars, you find even the boring zero-age main sequence stars exhibit strange mode instabilities if you go to high enough luminosities. So strange mode instabilities are found even for zero-age main sequence stars with masses above 80 solar masses. There are various strange modes, and the NAR approximation is, at least qualitatively, not too bad. Quantitatively, it's less satisfactory. And what has been done in the early years of discovery of strange modes instabilities in massive stars, instability has been considered along evolutionary tracks, and in fact, if the masses are high enough, then we found a variety of strange mode and strange mode instabilities, and we will look at these instabilities in detail in the following. Okay, so this is the result of a non-adiabatic stability analysis along the zero-age main sequence. L is equal to 0, so we consider spherically symmetric perturbations, and once we do the non-adiabatic analysis carefully enough, we see there are many modes crossing each other. There is the strange mode phenomenon, and there are crossings associated with high growth rates, with sigma I being negative, and here this is the mode seen here. This is the S1U. You have sigma I of the order of minus 0.2 or minus 0.3. So these stars become, these zero-age main sequence stars become strange mode unstable once the mass lies above around 80 solar masses. So even the boring zero-age main sequence stars exhibit strange mode instabilities if the mass is high enough, if the luminosity of course increases also with mass, and the luminosity to mass ratio increases once the mass increases. Luminosity goes roughly proportional to m cubed. That means that the luminosity to mass ratio goes with m squared. So this is the origin of strange modes or this is the situation with strange modes in ordinary main sequence stars. Well, concerning the NAR approximation, well, it seems that there are strange modes also in the NAR approximation, but once we compare the diagrams, the quantitative agreement is not that good. That means the conditions for the application of that approximations are not satisfied to the same degree as it's satisfied for the Wolf-Rayet stars, for instance. Now let's look what has been done concerning the investigation of the stability along evolutionary tracks. Here we have evolutionary tracks of massive stars. 20 solar mass, initial mass of course corresponds to 20 solar mass, initial mass 30, 40, 45, and we end up with 80 solar masses for the most massive stars. Okay, now we'll consider in a moment how does the modal diagram along such a evolutionary track look like, and we will start with the 20 solar mass object. 20 solar mass object and spherically symmetric perturbations. So this is the result, the modal diagram for spherically symmetric perturbations starting at the main sequence. This is the contraction phase, therefore we have this loop here, and this is the result of the linear non-adiabatic stability analysis. Whenever we have thick dots, the modes are unstable. Well, there is no indication, no real indication that there is some mode crossing or mode coupling present for this star, but it is still unstable, or it's unstable around effective temperature between log T 4.5 or 4.4. Actually, if we compare it to one of the classical pulsators, this is the 20 solar mass object is close to the beta Cepheid regime, so this actually might be interpreted as the kappa mechanism due to the heavy element abundances. So this instability strip enters the beta Cepheid regime. Now we increase the mass, and we end up, the next track we consider is the track of the 60 solar mass object with perturbation with respect to spherical perturbations. Now we see strange mode phenomena to appear. Well, there seems to be a lot of avoided crossings appearing here. There are modes crossing here in this regime. There seems to be a sequence of avoided crossings here. And, well, so we have the classical picture of strange mode instability in this diagram. Once we consider the growth rates, well, the growth rates are also in the dynamical regime, then we see, well, it seems to be that the growth rate has a first maximum here, a second maximum here, and a third maximum here. In a phenomenological way, one could associate these three maxima with the maxima of the opacity. Okay, and therefore These strange modes are usually, or are by some authors, are called the iron or the heavy element strange modes. This is the helium strange mode instability, and this is the hydrogen helium instability. So it's in a phenomenological way without reference to any physical explanation or physical process. They may be just grouped or classified as iron, helium and hydrogen helium strange modes. But it's strange mode instability, and the growth rates are pretty high. It's of the order of minus 0.1 or 0.15 even for this case. Okay, well, let's go back to this picture here, to the real parts. Well, what does this, if we ignore the low temperature part, what does this picture remind you? Or if you see this picture, what do you get in mind? Compared to something which we have discussed just a few minutes ago. It looks like, at least qualitatively, it looks like our subdivided, the pattern which is found for the subdivided organ pipe. So one might try, well, this is a fully non-adiabatic treatment. Let's try an adiabatic treatment of this part of the diagram. Let's see what we find. Well, adiabatic treatment, we have only neutrally stable modes. And how does the adiabatic treatment, at least for the high temperature part, look like? So same stellar models. Now we adopt the adiabatic approximation. Well, the helium and hydrogen strange modes are gone. They obviously do not have an adiabatic counterpart, but at least qualitatively, the pattern of the frequencies seems to resemble the pattern of the full non-adiabatic problem, and it still resembles that of the subdivided organ pipe. So what might have happened, or if the picture of the subdivided organ pipe is wrong or is applicable, then this run of these modes might be caused by a kind of diaphragm in the stellar envelope. The question is, which is the diaphragm, or where is the diaphragm in the stellar envelope? Well, to see this, we have plotted in the next plot here the run of the adiabatic sound speed as a function of radius for 3 different models of the previous diagram. And what we see, the sound speed is by no means a monotonic function, but it has a peak here. There is a peak or a maximum in the sound speed once we consider it for 3 models. Okay, this peak in the sound speed in effect may take the role of a diaphragm with high sound speed which decouples 2 parts of the stellar envelope. This peak in the sound speed is nothing but a way to decouple and to reflect sound waves at a certain position and to decouple 2 different parts of the stellar envelope. Now, once the star evolves, the relative position of this diaphragm, of this maximum of the sound speed, changes, and therefore, so to say, the length of the pipe changes. The length of the two acoustic cavities which are separated by this maximum changes. We see it from here to here. Well, this is the position of the diaphragm. Here the difference is much smaller than here between this maximum and the outer boundary. So the frequency which is associated with this part will decrease because the sound speed, or the sound travel time between these 2 positions becomes longer, and therefore 1 over the sound travel time the period becomes smaller. So if we plot the sound travel time between this maximum position and the outer boundary as a function of the model, then we obtain, or we should roughly get, the run of the frequency of the associated spectrum. We have done this. Well, this is the dashed line in this diagram, and we see the dashed line marks approximately the run of the mode which might have given rise to these sequences of avoided crossings. So what we have here and how we can interpret the modal diagram in this case for the massive stars is the maximum in the sound speed has decoupled or has split the star in two acoustic cavities, and the change of the position of this diaphragm will lead to a different behavior of the modes, a different run of the modes with the position of the diaphragm. One of the modes, like the organ pipe, one set of the modes increases because the acoustic cavity shrinks by change of position. The other cavity expands due to the shift of the diaphragm, and so one set of modes increases with evolution and the other set of the modes decreases with evolution. This gives rise to mode crossings which have unfolded into avoided crossings. So the naive and simple picture of the subdivided organ pipe helps us to understand what happens here in the massive star. Or going back then again to the original diagram, here it's even more obvious how these two sets of modes interact, the sets of modes going up there and going down here. So we have two acoustic cavities which are separated by a diaphragm, and the diaphragm, the position of the diaphragm shifts such that the frequency of one set of modes increases and the frequencies of the other set decreases, giving rise to crossings, and these crossings have unfolded into avoided crossings. Okay, that is an example how very simple models which can be generated without calculating anything. So this subdivided organ pipe model you can describe and graphically illustrate without having to calculate anything, and the transfer from this to the modal diagram observed or calculated for massive stars will give you a hint how these complicated modal diagrams are generated. Questions? Okay, now let's proceed further. Now let's have a look what happens if we now also allow for non-radial perturbations for models of the 60 solar mass object. Well, you see essentially the same picture. The low harmonic degrees lead to essentially a similar picture, but if you consider the growth rates of the iron opacity strange modes seem to have decreased, whereas the helium strange mode instabilities may have even increased in strength or have at least been unaffected. Okay, let's increase the harmonic degree even more to L equals to 10. Then you see that the iron strange mode instabilities have disappeared, whereas the helium strange modes are still there or even stronger. If we go to L equals 100, then the helium hydrogen strange modes are still there, are very strong, and they even extend towards the higher temperatures which have been occupied before by the iron strange modes. Okay, so once we insert the result now in our Hertzsprung-Russell diagram, we find the following result. We go back to the Hertzsprung-Russell diagram of the evolutionary tracks. That's here. And we denote those parts of the evolutionary tracks on which the models are unstable with a full line, and the parts of the evolutionary track which are stable, where no strange mode, no instabilities were found with the dotted lines. We find that there is a small range in temperatures which is unstable for low masses. This range of models extends and goes even to the main sequence. So it even hits the main sequence. The very thick lines, by the way, correspond to extremely strong instabilities. So whenever we have a very thick line, then the instability exceeds a certain threshold. So for masses above 60 solar masses, we essentially have instability along the entire evolutionary track. Well, the dashed lines appearing here in this diagram is the so-called Humphreys-Davidson limit. It comes from observation and denotes a region in the Hertzsprung-Russell diagram where no stable, no non-variable star is found. So above this Humphreys-Davidson limit, above this dashed line, we do not have static hydrostatic stars, we do not have non-variable stars. So this part of the Hertzsprung-Russell diagram seems to be forbidden for hydrostatic or stationary stars. And well, this region is covered by the iron strange modes, and this domain is covered by the helium and hydrogen strange modes. You already see here that the bottom of this Humphreys-Davidson limit approximately is compatible with the stability limit, which we derive here. This is the 50 solar mass star is the track of the 50 solar mass star is around coincides roughly with the bottom part of the Humphreys-Davidson limit. All the tracks above are stable. So this is expected to depend, of course, the iron strange modes on the iron opacity. So if we go to a study with low metallicity, we expect this part of the stability diagram to be affected. In fact, this is the case. So if we reduce the metallicity, the chemical composition, then we end up with the following Hertzsprung-Russell diagram. Full lines are unstable branches, dotted lines are stable branches, and we see anything to the left of the Humphreys-Davidson limit, which is covered by the iron strange mode, has now become stable. That's because the third opacity peak due to iron group elements is missing. But remarkable, the onset of instability for the helium and later on for the hydrogen instability coincides with the Humphreys-Davidson limit. So some people, including myself, have claimed that the instability limit we derive has something to do with the Humphreys-Davidson limit, or might be possibly an explanation of the Humphreys-Davidson limit, because the instabilities, the strange mode instabilities, which are independent of the metallicity, of the chemical composition of the star, which are defined by helium and hydrogen strange modes, they essentially cover the domain which is found to be empty with respect to stable, to stationary, non-variable stars. Okay, so these are pretty robust, these instabilities. They do not have an adiabatic counterpart. They are not affected by metallicity or chemical composition, because of course helium and hydrogen is the composition of hydrogen and helium is essentially fixed by primordial abundances. Okay, in a little bit different representation, here in red the unstable domain. Here it hits the 0H main sequence. Here we go into the beta Cepheid regime, And this part is not found once we reduce the metallicity, and the bottom of this line here is defined by, or coincides with approximately with the Humphreys-Davidson limit. Well, for small metallicity, we still have a coincidence of the instability domain and the left branch of the Humphreys-Davidson limit. Down here it fits not that nice. Nevertheless, it seems, or we suspect there is some relation to the Humphreys-Davidson limit. Okay. Now let us summarize the properties of the various iron, hydrogen, and helium strange modes. Well, I haven't covered the point that the treatment of convection might be crucial in some cases to the results of the instability or the stability calculations. The iron strange modes are sensitive to the treatment of convection. The helium and hydrogen strange modes are insensitive. Well, dependence on metallicity, of course, the hydrogen, helium are insensitive. Dependence on metallicity, of course, iron strange modes depend on metallicity. Well, the harmonic degree for which these modes exist is L smaller than 10 for the iron strange modes, and L smaller than 500 for the helium strange modes. The maximum growth rate is found for the iron strange mode at spherical symmetric perturbation, and around L equals 100 for the hydrogen strange modes. Well, for the hydrogen and helium strange modes, the kappa mechanism is not responsible. These are strange modes. For the iron strange modes, partially we have the kappa mechanism, but there are also strange modes instability responsible for the instability. Temperature range, of course, for the hydrogen and helium strange modes, log T is smaller than 4.3, and for the iron strange modes, the log TF is bigger than 4.3. We have found the iron strange modes might have a stable adiabatic counterpart, whereas this is not the case for the helium ones, and the helium strange modes have an NAR counterpart, and the iron strange is partially yes. Okay, this is a summary of the strange modes appearing in massive stars. Well, finally, I would like to comment a little bit on a model for strange mode instabilities. So far we have just provided some conditions, some necessary conditions, which are found once we calculate strange mode instabilities. And one of these conditions for occurrence is that luminosity to mass ratio is bigger than 10 to 3, and that the ratio of thermal to dynamical timescales for a large fraction of the envelope should be smaller than unity. However, these conditions do not provide a simple intuitive model. Well, I'm not sure whether I will be able to provide or to present you now a simple enough model for strange modes, but these conditions are certainly not a direct simple model for do not provide a simple model for strange mode instability. So, well, let's summarize what we know about the occurrence of strange modes before we go to discuss a simple model for the strange mode instability. So, luminosity to mass ratio bigger than 10 to 3, short thermal timescales means radiation pressure is dominant. The strange modes occur both for radial and non-radial geometry, so geometry itself is not essential for this process. Well, they operate on dynamical timescales, so even the growth rate is dynamical, they do exist in the NAR approximation, and this may raise the question whether they are of mechanical origin. They certainly cannot be of thermal origin because they exist in the NAR approximation, which means they exist without heat capacity. Okay, so for a model, we can adopt the following properties. Well, geometry is not essential, so we take the simplest geometry we can think of. This is plane geometry. Well, obviously also the consideration of the gravitational potential is not essential, so we adopt Cowling's approximation. Perturbation of the potential is neglected. Then we know the instabilities occur in the NAR approximation. That means we can assume that the luminosity perturbation vanishes. Well, if they exist in NAR approximation, the luminosity perturbation is not essential, and we can assume that the luminosity perturbation is zero. Well, then we found that in the configuration or in the situations when the strange modes appear, the contribution of gas pressure is small. That means the ratio of gas pressure to total pressure is close to zero, or we can consider the limit of negligible gas pressure, limit of beta going to zero. Okay. So what we are to justify it here, again, the ratio of thermal to dynamical timescale. It's small for the 24 solar mass object, and it's big for the 60 solar mass object. We have seen and discussed this diagram before. And the other diagram is the ratio of gas pressure to total pressure for the 60 solar mass object. The contribution of gas pressure is always above 10%, whereas for the 24 solar mass object, it falls below 10%. Okay? So let us construct now a model for strange mode instabilities based on these simplifying approximations. Well, we have of course, we have to do correctly the mechanical equations. We cannot apply any approximation to them, and the first equation which we need to consider is mass conservation in the Eulerian picture. That means the derivative of time, the derivative with respect to time of the Eulerian density perturbation is given by is given essentially by the divergence here in the one-dimensional model by d by dx of rho naught times the perturbation, Eulerian perturbation of the velocity. Well, the momentum conservation equation is, we have discussed similar problems for the organ pipe already, is given by rho naught times the derivative or the Eulerian derivative of the Eulerian perturbation of the velocity, which is equal to the gradient of the pressure perturbation plus gravity times the density perturbation. Well, if we combine these two equations, we end up with the one-dimensional acoustic wave equation. We have seen this several times, and now to close this system we have to apply, or we have to adopt, a relation between pressure and density perturbation. Usually in the common adiabatic approach we assume that pressure is a function of density only. This means that the perturbation of pressure is given by sound speed squared times the density perturbation, and what that means physically is that concerning if you're considering a wave with a wave representing the pressure perturbation and a wave representing density perturbation, that these waves are in phase, because pressure perturbation is proportional to density perturbation. There is no phase lag between pressure and density perturbations. Okay. Well, once we adopt the NAR approximation, with this, of course, if we apply this relation of this form to the mechanics, to the acoustic wave equation, we will not get instabilities. It's simply an adiabatic. It will be an adiabatic system, and what we need to generate these instabilities is a deviation from adiabaticity. Okay, so what shall we do instead? We adopt first the NAR approximation. The energy equation is satisfied with vanishing luminosity perturbation. This has been seen already. We have already adopted this. And then the only relation which can provide a relation between the pressure and density perturbation is then provided by the remaining equation, which is the equation for energy transport. The energy transport equation is here written as a relation between the gradient of the radiation pressure and the luminosity. So gradient of radiation pressure is minus opacity times density times luminosity over 4 pi CR squared. Now let's perturb this quantity, this equation. What are we left with? Linearization of this would result in, well, on the left-hand side we are left with the gradient of the perturbation of the radiation pressure. On the right-hand side we have to perturb kappa times rho. This gives kappa sub rho. It's the derivative of kappa with respect to density, plus the perturbation of density gives the 1 rho Eulerian perturbation of density over the stationary value. And we have to take into account that kappa also depends on the temperature, or alternatively on the radiation pressure. So we have kappa sub p rad times the perturbation of the radiation pressure relative to its stationary value. We are in the Eulerian picture, so R is the independent variable, no perturbation required, and L is assumed to be constant. Now, now we consider, in addition to the previous assumption, we consider the limit of high wave numbers. That means if we assume, or if we do a local analysis, then the gradient goes with k times the gradient in the high wave number local analysis is proportional to wave number times the perturbation of p rad. This is to be compared to this term. Now if k is large, then we may neglect this term with respect to the gradient. If we consider high wave numbers, then and which means we are assuming perturbations of the following form: x I k r, and k is assumed to be big than dp rad by dr is ik times p rad tilde, and we have to compare this term with this term. This means for high wave numbers we can neglect this term with respect to the gradient. So we are left with the final result. The derivative of the perturbation of the radiation pressure is essentially given apart from the stationary value by kappa sub rho plus 1 times the density perturbation. Well, if we now assume the limit that gas pressure goes to 0, then the radiation pressure is equal, or in this limit the radiation pressure becomes equal to the total pressure. So we can drop the index rad here, and we have dp by dx, dp tilde by dx is 1 over rho times dp by dx times kappa sub rho plus 1 times the density perturbation. Now, what does it mean concerning the phase difference between the pressure and the density. If we have a pressure, the dependence of pressure like a wave, x IKR, what does it mean? Well, are pressure and density perturbation in phase due to the, well, if you take it in a real representation, cosine KR for the pressure. Of course, if we differentiate the cosine once, then we have a phase lag of pi halves. Okay, so what that introduces in the pressure density relation, it introduces a phase lag between the pressure perturbation and the density perturbation. Okay, so in the limit of dominant radiation pressure, we have this relation finally for the relation between pressure and density perturbation. Okay, now we insert this relation instead of the P tilde being proportional to C squared times rho tilde. We insert this relation into the acoustic wave equation. Well, phase lag. And then we end up, if we insert this in the wave equation, then we end up with the second derivative of the density with respect to time minus the first derivative of the quantity gravity kappa sub rho times the density, the Eulerian density perturbation. Now, for plane waves and a local analysis, we write rho tilde as an exponential of ikx plus I omega t. Then this gives this d by dx gives by the derivative with respect to x gives an ik at this position and gives a minus omega squared for the second time derivative of the density perturbation. And we are left with omega squared is minus ik g gravity times kappa sub rho. Or, well, what does it mean for stability once we take the root, or once we once we consider k to be a real quantity? Omega squared, or omega, is always a complex function, and it's always complex, and we always have instability. So here we arrive at the result that we found a local dispersion relation which automatically provides us with an instability, and this might be or could possibly be the origin of strange mode instability. Remarkable is that this dispersion relation is usually that of gravity waves. So omega squared being proportional to the wave number is typical for gravity waves, but we are dealing with sound waves, with strange sound waves. So these strange sound waves seem to behave like gravity waves. When gravity waves, we have ik times gravity times the entropy gradient. So kappa sub rho plays the role of the entropy gradient of a gravity wave. You have no gravity waves. This is a sound wave where kappa sub rho is responsible for a non-zero kappa sub rho is responsible for instability. Moreover, you see, it does not depend on the sign of kappa sub rho, whether we have instability. We always get instability, and we always also have, together with an instability, we also have a damped mode. So kappa sub rho must not be zero for an instability, otherwise it is irrelevant whether the sign of kappa sub rho is positive or negative. And we find a situation where kappa sub rho is responsible, non-zero kappa sub rho is relevant for instability, but kappa sub t is completely irrelevant. This is in contrast to the kappa mechanism, where kappa sub t determines the instability, and we even need a special sign, a positive sign of kappa sub t, to have the kappa mechanism instability. Okay, now finally, well, the question is, can we test whether this dispersion relation plays a role or not? Well, we have seen it does not depend on the sign of kappa sub rho, but it depends on the fact whether kappa sub rho is 0 or not. Do we have situations where the derivative of kappa with respect to density is 0 in a star? When do we have kappa sub rho is 0? Which source of opacity has the property that kappa sub rho is 0? Well, there is one source of opacity which implies a constant opacity, constant with respect to temperature and pressure or density. This is the Thomson scattering or the electron scattering of photons. This is always present, so if the star is hot enough, if we take a hot enough star, then we will end up with electron scattering. This is constant, and electron scattering has kappa sub rho equal to 0. Now the problem is, even if the star is hot enough, well, if it includes, or if the chemical composition includes a finite heavy element abundance, then the internal transition of the heavy elements will lead to an opacity bump. But what happens if we get rid of these metals, or if we assume a star having no metallicity? Then if the star is hot enough, helium and hydrogen are completely ionized and do not contribute to the opacity, and only the electrons contribute to opacity. That means kappa sub rho is 0 once we have a hot enough star which does not have any metals. Do such objects exist? Well, these are the so-called population 3 stars. These are primordial stars, which are the first generation of stars after the Big Bang, because heavy elements need to be produced by stars. And once this is the first generation of stars, we don't have metals. So these population 3 stars could be objects by which we could test whether this dispersion relation is correct, and whether this representation is correct for the strange mode instability. So, well, Thomson scattering has kappa sub rho equal to 0, and if we don't have metallicities and the stars are hot enough, so this means 0H main sequence population 3 stars are hot enough to have the complete helium and hydrogen ionized, and they do not have metals which could contribute to the opacity. Okay, so that's what we have done, and Professor Yadav was part of this study. This is a modal diagram for population 3 stars. You see the chemical composition: hydrogen 77 and helium 23%, and this is the modal diagram for a 200 solar mass stars with a luminosity of log L over L sun 6.77. So what we see here is, so this star is should be affected by strange mode instability in any way, because it has high luminosity to mass ratio. This star inevitably has strange mode instabilities. But what we see here is we find strange mode instabilities, but only below log TF 4.4. If we go to higher effective temperatures, there is no strange mode instability, which means, or which is caused by the fact that once the temperature is higher than log TF 4.4, the hydrogen and helium is completely ionized, and the only source of opacity for hotter stars is the electron scattering, and we do not expect strange mode instabilities above log TF 4.4. To show you also the modal diagram here, well, we have strange mode instabilities below log TF 4.4. These are the hydrogen and helium strange modes, but we do not have the iron strange modes, because then the opacity is missing for the iron, and the opacity is in fact constant. Kappa sub rho is constant, and therefore we do not have strange mode instabilities. In other words, this result, or these calculations support the idea that the dispersion relation we have got here might be relevant for strange mode instabilities, and we might be able to explain strange mode instabilities on the basis of this dispersion relation. This might be an ingredient for further studies of the instability. Well, to finish with that, we can use our findings that for adiabatic changes of state, density and pressure are in phase, whereas here we have taken a relation between pressure and density perturbation which are out of phase by pi half. This means this an intuitive understanding may be gained that the restoring force in our wave, in our acoustic wave, is caused by a phase lag between the restoring force and the density. Consider a pendulum. Once you want to excite or increase the amplitude of a pendulum, then the exciting force should come in the right phase. Once the displacement of the pendulum is zero, you should have the biggest force. That means that the force is maximum when the displacement is minimum. So there should be a phase lag of 90 degrees or pi halves. The displacement of the pendulum can now be related to the density perturbation and the force to the pressure perturbation, and it means the ideal case for an instability to occur would be that pressure and density perturbation have a phase lag of pi halves. So we end up in that sense with the intuitive understanding, well, that we have an instability if the external force, which corresponds to pressure perturbation, lags behind the displacement, which is the density perturbation, and that's actually achieved by providing the relation between pressure and density perturbation by the equation of energy transport. Okay, so finally let's summarize. Well, let's summarize our chapter on strange mode instabilities. Well, main point, they exist for short thermal timescale, they are of mechanical origin, they occur for dominant radiation pressure, and the local dispersion relation in the limit of low gas pressure and low thermal timescale is given by omega squared is minus ikg times kappa sub rho. Kappa sub rho is necessary for this instability, and this is supported by our findings that in fact for POP3 stars we have Thomson scattering atmospheres once the stars are hot enough, and for these population 3 stars we do not have strange mode instabilities, at least in the initial phase, or in their initial phase of evolution close to the 0 H-main sequence. Okay, so that's the these are the final statements concerning strange modes and strange mode instabilities. Maybe we can tomorrow have a look at an example, a recently studied example, which includes the group of yellow hypergiants. And with this recent study, we can then finally close this chapter, and we will then turn to nonlinear simulations of the evolution of an unstable star. So thank you very much for today, and we'll meet tomorrow then to the final two lectures and sessions.